Hello, and welcome to this tutorial. And this is a tutorial for ICC 2021. The title of the tutorial is Online Learning for Wireless Communications, Theory, Algorithms, and Applications. My name is Cong Xian. I'm an assistant professor at the University of Virginia in the Department of Electrical and Computer Engineering. This is a tutorial that will be given by me and Professor Chem Tekin from Belkent University and Professor Mihaela van der Schaar from University of Cambridge, the Alan Turing Institute, and UCLA. So let me start this tutorial by give a very brief overview of what this tutorial is about, and I will also introduce the outline of the entire tutorial. As the title suggests, this presentation is about using online learning for wireless communications. And this obviously is one of the very hottest and very important recent research directions in the wireless networking and wireless communication research. And largely, this is motivated by the unprecedented network complexity that we are observing today. Instead of having a simple cellular system that supports voice and maybe some data service like a few generations ago, nowadays we are seeing this heterogeneous type of networks supporting all kinds of different applications with different requirements. And to maintain and optimize such networks, it becomes increasingly difficult to rely on the traditional methods. And that motivates the adoption of online learning. So here I put one kind of a line of question here. It's a maybe billion-dollar question. How can we actually have adaptive, automated, and autonomous optimization of multiple, not single, heterogeneous network entities that can learn, match, and evolve with the system dynamics while only observing very limited information about the environment? This is the main theme of this entire tutorial, and this is also why we believe online learning is the right tool. That is the tool that should be known by every wireless engineer nowadays. Okay, so the need for online learning. Again, to understand why we need online learning, we have to go back to what the previous design really does. Previous design philosophies is becoming increasingly insufficient. Again, we have relied significantly on optimization methods, and solving such optimization problems has made significant progress in terms of the theory and applications of on the optimization side. And as a consequence, engineers can rely on those methods to optimize their system. However, this method is becoming difficult to adopt, to put it mildly, mainly because, first of all, the system is too complicated to be formulated as a simple optimization problem. Secondly, if we stick to the optimization approach, once the system environment or the dynamics change, we have to rerun the optimization method. And last but not the least, in order for optimization-based method to work, you have to have the environmental information or the system information. So you have to basically have an information collection phase. All of this add to the burden of using this type of approach. The second is something that is often used in industry, which is the engineering heuristics. And this is mostly by the domain expert of the network who knows the inside out of how the network works. And then they can often identify certain issues, what we often call corner cases in the industry, and then try to solve these corner cases. And this is a very inefficient approach because it often requires significant labor from the human perspective. Also, solving corner cases typically only solves the problem at hand and does not really automatically take care of what's going to happen in the future. Last but also not the least, many corner cases are often conflicting with each other. So it's difficult sometimes to just find a good solution that works for all cases. The last one is something that is also relatively new, which is to use machine learning, more specifically supervised learning. So for example, the deep learning using deep neural networks. And this can be viewed as a data first, model later type of approach. So basically, we are collecting data from the network. And then based on this data, we are training certain machine learning methods And then we do inference using the trained models. This approach works when the system is relatively stationary. And we have seen that typically when the system has high dynamics or it evolves over time, this approach has some common shortcomings as the previous two methods. So fundamentally, the issues we are facing here, I summarize 3 points. One is the extremely complex wireless system. Second is the unknown and highly dynamic deployment environment. And the third is this coupling behavior that actually, for example, relates multiple KPIs, or the non-convexity of the optimization problem, or the computational complexity of certain algorithms that just do not scale with the system dimensions. With that, let me go to the online learning. So what is online learning? If you just look up the definition, let's say from Wikipedia, online learning is a method of machine learning in which data becomes available in a sequential order and is used to update the best predictor for future data at each step. So this definition is very general, but the two key things I want to highlight here is that, first of all, this is a sequential operation. Secondly, this sequential operation operates at multiple steps. Our tutorial will not focus on the very generic definition of online learning, but rather we will focus on sequential decision-making under uncertainty. This is intimately related to the applications in wireless communications, as we will see later in this tutorial. And more specifically, we will mostly talk about two specific tools in this field. One is multi-arm bandits. The second is reinforcement learning. Okay, so with the introduction of online learning, now let me explain a little bit why should we consider online learning for these wireless communication problems. First of all, the characteristics of online learning match very well with the wireless communications. In wireless communications, often, especially in certain network management, let's take that as an example, we have a closed loop situation and we have sequential operations. For example, when you want to optimize certain network, generally speaking, you would start the network. You start operating the network with, let's say, a default set of parameters. And then you kind of, collect the KPIs from, let's say, the users or the base stations or some other devices in the network. You evaluate the performance of the network, and then you tune the parameters, and then you continue to evaluate until the system gradually converges to a state that you like. So this is a closed loop and sequential operation that matches exactly with what online learning does. Secondly, it relates to the performance criteria. In wireless communications and wireless networking, we often look at the long-term performance. We're not specifically worried about an immediate, let's say, low data rate, but rather, if my data rate is low for a consecutive period of time, then I may need to actually change my network configuration. So long-term performance is also a key feature in online learning, where it is difficult to guarantee at any given time instance the performance of the algorithm, but rather we will be able to guarantee the long time average performance of the system. Lastly, for online learning to work, generally we need feedback. This sequential decision making with uncertainty relies on when you take a certain action, you would be able to observe something that is a consequence of the action you just took. That requires feedback protocol. In some other applications of online learning, this feedback protocol is actually the bottleneck of the system. But fortunately for wireless, we have very well-designed feedback protocols in place. We know how to, the system allows you to collect KPIs, the user equipments or the UEs would report back their measurements. You get all kind of, feedback information from the system. So this is really a plus when you try to apply online learning to this type of problems. Okay. So to summarize, today's wireless systems have much stronger capabilities, and we are in a prime place to really adopt online learning techniques to solve this type of problems. The second part is basically online learning is ready to contribute to our problem. Online learning has matured over the past decade, especially. The topic itself has a long history. It actually dates back to the 1930s when the first paper multi-arm bandit, for example, appears. However, this technique has attracted a lot of interest over the last decade, and many progresses have been made. And especially this notable advances in multi-arm bandits and reinforcement learning, both in theory and practice, put us in a good position to consider this tool for wireless communications. In addition, new methods such as deep reinforcement learning also have seen success in many other applications, such as speech recognition, computer vision, NLP, and computer games. So it's also natural to explore whether they can be applied to wireless communications. We are not the only one, obviously, who have attempted to introduce online learning to wireless communications. In fact, if you look at just the conference papers, let's say for ICC 2021, you will see many papers, trying to use reinforcement learning, multi-arm bandits to solve communication or wireless problems. But for now, I would say it's more reasonable to claim that online learning has flashed promises in solving complex wireless communication problems, and we'll give some examples here. But I will also highlight the fact that I think there is a long way to go when we want to make this tool effective and easy to use for the engineers in the industry. Okay, so let me give a quick outline of the tutorial. So the tutorial will be 4 parts, okay? So this is the first part, the overview of online learning for wireless communications, which is delivered by me. And then we will have 2 parts, part 2 and part 3, focusing on the 2 tools I just mentioned. Part 2 is about multi-arm bandits. This will be a 1-hour tutorial by Chem Tekin, who is an expert in MAB. And part 3 is about reinforcement learning. This will be roughly a 50-minute presentation by Professor Mihaela van der Schaar, who has done tremendous work in this area. And the last part will again come back to me. I will give some design examples in wireless communications using the tools of online learning. And I will also try to conclude this entire tutorial. Okay, so that's all for the opening part, and I hope you would enjoy this tutorial. Thank you.
Hello, everyone. I am Cem. I am an associate professor in the Department of Electrical and Electronics Engineering at Bilkent University. In this part of the tutorial, I will talk about multi-arm bandit problems and their applications in wireless communications. So I will start by introducing the multi-arm bandit problem, the notions of regret and how we can design efficient policies for this problem. Then I will consider an extension of the multi-arm bandit called combinatorial multi-arm bandit problem and talk about its applications in wireless communication. Then I will talk about decentralized multi-user multi-arm bandits. Finally, I will talk about other bandit models like contextual bandits. Now I will start the first part, which is introduction to multi-arm bandit problem. I will first formulate the problem, give some examples. I will discuss the notion of performance, which is the regret. Then I will show how we can design policies that minimize the regret. And I will end with comparison of different policies and discussion. So the multi-arm bandit problem is the problem of gambling in a casino with K slot machines. These slot machines are also known as arms, sequentially over rounds. When played in a round T, an arm yields a random reward that comes from a fixed but unknown distribution. So in each round, the learner plays an arm based on its previous arm selections and previous reward observations. Then it observes and collects the random reward of the selected arm. The goal of the learner is to maximize its expected cumulative reward. One application of multi-arm bandits in wireless communications is dynamic channel selection. Consider a time-slotted communication system where time is indexed by phi. There are K channels with time-varying qualities. Channel gains and distributions are unknown beforehand. In each time slot T, the user selects a channel based on its previous channel selections and reward observations. It transmits on the selected channel, then observes a feedback as the reward, which could be ACK or NACK. The goal is to maximize the expected number of successful transmissions by learning to choose good channels. Another application is beam alignment. Again, we have a time-slotted communication system. There are cane beams with time-varying qualities. Each beam results in an unknown expected received signal strength. On each time slot, the learner selects a beam based on previous beam selections and previous reward observations. The learner transmits with selected beam. At the end of the round, it observes a reward which is equal to noisy RSS. The goal in this case is to maximize the expected cumulative RSS. So here is a formal description of the multi-arm bandit model. I will first describe properties of the bandit environment, what is known and what is not known. The learner knows the set of arms, K. The learner knows arms are independent. The learner doesn't know the reward distribution of the arms, but the learner can know the distribution type, such as arms with Bernoulli rewards or Gaussian rewards. But the learner does not know the expected rewards of the arms. Next, I will describe an environment class. Environment class includes a class of bandit instances. For instance, example A, it could be all K-arm bandits with Bernoulli rewards, but the parameters are unknown. Example B, it could be all K-arm bandits with rewards in the unit interval. In other words, rewards with bounded support, but distributions are unknown. In this tutorial, I'll mostly consider cases A and B, but other cases include sub-Gaussian rewards, or heavy-tailed rewards. How does the learner select actions? The learner needs to follow a policy. The policy takes as input the history of the learner, which consists of all past selections and reward observations of the learner. The policy maps histories to distributions over arms. The learner follows the policy in each round. It plays an arm sampled from the distribution dictated by the policy. It observes the noisy reward of the played arm. Then it updates its history for the next arm selection. Recall that the goal of the learner is to maximize its cumulative expected reward. What is the best possible? If the mean rewards are known, then the best arm is the arm with the highest expected reward. In this case, we denote it by arm A star, and we denote the highest expected reward with mu star. So the highest cumulative expected reward can be obtained by playing always the best arm. For T rounds, it is equal to T times mu star. The regret of the learner is defined as the difference between the highest expected reward that could be obtained in T rounds and the expected reward that the learner can obtain by selecting arms according to its policy. So every time the learner makes a mistake, it will incur regret. So regret is something that is non-decreasing over time. The fact that maximizing the expected cumulative reward is equal to minimizing the regret. So we seek to find policies for the learner that minimizes the growth rate of the regret. So what is a good policy? A good policy achieves a time average regret that goes to 0 in the limit for all possible bandit instances in the bandit class we have. For instance, a good policy can incur regret that grows with square root of t, or regret that grows logarithmically over t. In this case, in the limit, time average regrets will approach to 0. In order to achieve small regret, a good policy should trade off exploration and exploitation. It should explore arms to discover the best arm. And at the same time, it should exploit the arm it believes to be the best to maximize its cumulative reward. Orthogonal to this, a good policy should also be computationally efficient, because these policies are deployed by users in the wireless scenario devices with limited computation and memory abilities. So in the K-arm bandit problem, there is a well-known regret decomposition, which relates the regret with the number of times bad arms are played. For this, let delta A represent the difference between expected reward of the optimal arm and arm A. That is called the suboptimality gap. Arms with positive suboptimality gaps are suboptimal. Let NAT represent the number of plays of arm A by round T. The regret decomposition lemma tells that the expected regret is equal to sum over all arms, suboptimality gap of the arm, times the expected number of plays of the arm. This is intuitive since every time we select the suboptimal arm A, we will incur an expected regret proportional to its suboptimality gap. Next, I will define a consistent policy. So a policy pi is consistent if for all bandit instances in the environment class we consider, and for all positive p, the expected regret divided by t to the power p, and the limit goes to 0. In other words, consistent policies incur very small regret for all bandit instances. Next, I will show you a negative result, which gives an asymptotic lower bound on the achievable regret. This result is by Lau and Robbins. So let E be the class of bandits with independent single parameter exponential family of reward distributions. For instance, bandits where arm rewards are Bernoulli with unknown parameters theta A. In this case, any consistent policy incurs regret that grows at least logarithmically over time. This means that any consistent policy should explore suboptimal arms at least logarithmically many times in order to minimize its regret. The constants that appear in the asymptotic lower bound depend on the suboptimality gap and also the KL divergence between the distributions of the optimal and suboptimal arms. Now, with this lower bound, we know that the smallest regret that could be achieved grows logarithmically over time, and policies which achieve the regret lower bound are called asymptotically optimal. So this is a notion of optimality that holds in the limit. It doesn't give insights about the finite time performance of the policies, which we are more interested in practical applications. There is another definition of optimality called order optimality. So order optimality says that policies which achieve expected regret that grows logarithmically over time are order optimal. So this is a weaker sense of optimality. Next, I will describe policies and what type of regrets they achieve. We'll try to construct regret minimizing policies. First of all, let's consider a greedy policy. The greedy policy stores and updates cumulative rewards and play counts for each arm. Initially, it samples each arm once. Then at each round, it selects the arm with the highest sample mean reward. It collects the reward of the selected arm and uses this reward to update the parameters of the selected arm. Obviously, the greedy policy always exploits, it never explores. Therefore, it might get stuck selecting a suboptimal arm. Therefore, it incurs linear regret in the long run. Our next goal is to design policies that can explore efficiently to avoid getting stuck in suboptimal selections. One such policy is the UCB policy. UCB means upper confidence bound. This policy again stores and updates cumulative rewards and play counts for each arm. Initially, it samples each arm once. Then at each round, it calculates the UCB index for each arm, which consists of two terms. The first term is the sample mean, and the second term is the exploration bonus. The exploration bonus is inversely proportional to the number of plays of an arm. So if an arm gets played a lot of times, the exploration bonus is going to diminish. After calculating the indices, the policy at each round plays the arm with the highest index. Then it collects the reward of the played arm, and it uses it to update the parameters of the played arm. Next, I will show how to bound the regret of UCB. The first lemma shows that the index of each arm is actually an upper confidence bound on the true mean reward from that arm. This holds with high probability. In other words, the algorithm considers the best possibility for each arm by assuming that its unknown true mean reward is actually equal to its index. Next, I will argue why this policy will not select suboptimal arms too often. For that, assume that a suboptimal arm is selected, then the following chain of inequalities should be satisfied. The index of the selected arm is at least the index of the optimal arm, but that is at least the true expected reward of the optimal arm, which is greater than the true expected reward of the selected arm. We argue that a suboptimal arm A cannot be selected too often, because if it is selected too often, then its index should converge to the true mean. But this cannot happen a lot, since its true mean is less than the true mean of the optimal arm, which is less than or equal to the index of the optimal arm. So one can use this idea in order to prove that the UCB policy plays suboptimal arms only logarithmically many times, and we get the following bound on the expected regret of UCB. So as you see, there's a summation over all suboptimal arms, log t over the suboptimality gaps of the suboptimal arms. So this shows that UCB achieves an order optimal regret of log of t. Here are the main messages. The algorithm is order optimal, but the regret is inversely proportional to the suboptimality gaps, which means that if the gaps are small, then suboptimal arms are harder to distinguish than the optimal arm. We will spend a lot of time trying to explore these suboptimal arms, which will result in higher regret. The UCB achieves exploration by using the principle of optimism under uncertainty by believing that its unknown true mean is equal to the index for each arm. Another property of the algorithm is that the arm recommendation is deterministic given the history. This illustration shows how UCB selects arms over time. In the x-axis, you see the arm probabilities, and you see the three arms. So you see as time goes on, the selected arms, the rewards received from the selected arms, and how the upper confidence bounds evolve. This figure shows, in addition to the upper confidence bound, also the lower confidence bound. So the region between the upper confidence bound and lower confidence bound is the confidence interval, which contains the true unknown mean with a high probability. As you see, the optimal arm is selected more often than the other arms, which results in confidence interval of the optimal arm shrinking much more than the confidence intervals of the other arms. Next, I will talk about another algorithm that minimizes the regret. This algorithm is called Thompson sampling. It is also known as posterior sampling. This is a Bayesian algorithm that is introduced by William Thomson in 1933. It is also the first bandit algorithm. The algorithm starts with a prior over bandit instances. At each round, it computes the posterior distribution of the optimal arm by conditioning in the history. And it samples an arm from this posterior distribution and plays it. There is an equivalent way to perform Thompson sampling. We start with a prior over bandit instances, compute the posterior over bandit instances. Then we sample a bandit instance from the posterior and select the arm that maximizes the expected reward in the sampled bandit instance. I will explain in detail how to perform Thompson sampling for Bernoulli bandits. In Bernoulli bandits, arm rewards are Bernoulli. Bernoulli parameter for arm A is theta A. It is not known by the learner. It is assumed that the arm rewards are independent. The learner starts with a prior over theta A for each arm, which is the beta 1,1 distribution. This is equal to the uniform distribution in the unit interval. The learner can compute a posterior distribution for each arm. The posterior distribution is also beta, with parameters 1 plus alpha and 1 plus beta. Here, alpha represents the number of successes from past plays of arm A, and beta represents the number of failures from past plays of arm A. So the Thompson sampling algorithm stores and updates for each arm the success and failure counts. At each round, it samples from the posteriors of each arm, and it compares the samples, and it selects the arm with the highest sample. Afterwards, it collects the reward of this selected arm, and it updates either the success or failure probability based on the reward. This theorem shows that Thompson sampling achieves the optimal growth rate of the regret. You see that the regret increases logarithmically over time. It is also proportional to gap of each arm divided by the KL divergence between distributions of suboptimal arm A and optimal arm. The KL divergence is lower bounded by a function of the square of the gap. This allows us to compute a bound on the regret of Thompson sampling that only depends on the gaps. And this bound is actually the same as the UCB bound. So the main messages from this algorithm is that Thompson sampling achieves asymptotically optimal regret, since its regret bound achieves the optimal dependence on the problem parameters as indicated by the bound of Lai and Robbins. It achieves exploration by sampling from the posterior distribution of each arm. Different than UCB, Thompson sampling is a randomized policy because its selection given the history depends on the samples of the posterior. This slide shows an illustration of how Thompson sampling works over time. So as you see, in each round, the algorithm samples from the posterior distributions of the three arms and picks the arm with the highest sample. As time goes on, you see the posterior distributions of the selected arms are updated. And in this case, the red arm is the best arm. And Thompson sampling selects it most of the time. But we also see that it occasionally explores other arms in order not to miss any optimal arm. The next slide compares UCB and Thompson sampling in a 10-arm bandit problem. There are 8 arms with expected reward 0.8, 1 arm with expected reward 0.94, and 1 arm with expected reward 0.95. The rightmost arm on the rightmost figure is the optimal arm. We see that both UCB and Thompson sampling selects the optimal arm the highest amount of times. It seems that the time average cumulative reward of Thompson sampling is higher than the UCB algorithm. From the right figure, we also observed that the arm with the expected reward 0.94 is also selected a lot by both algorithms. This is happening since the gap of that arm is small. Both Thompson sampling and UCB needs to play that arm a lot of times to distinguish it from the optimal arm. So in practice, it is known that Thompson sampling works very well. However, there are variants of the UCB algorithm that also work very well. These algorithms are based on tighter upper confidence bounds, hence they can achieve smaller regret. One example is the KL-UCB algorithm. So far, I talked about regret bounds that grow logarithmically over time and that are inversely proportional to the suboptimality gaps. These are called gap-dependent bounds. When the gaps are small, these bounds diverge. There is another way to prove regret bounds for UCB and Thompson sampling. They are called gap-free bounds. Essentially, they hold for any bandit instance. And one can show that UCB and Thompson sampling also achieves regret in the order of square root of KT log T, where K is the number of arms. There is no dependence on the problem structure or delta in these bounds. This is also related to the notion of minimax regret, which is basically infimum overall policies and supremum overall bandit instances the expected regret. And it is known that the minimax regret for the k-arm bandit grows in the order of square root of k times t. So this shows that both UCB and Thompson sampling are nearly minimax optimal. Next, I will give a brief comparison between the general reinforcement learning and the multi-arm bandit problem. In the general RL framework, an agent repeatedly interacts with an environment by choosing actions which are arms of the bandit. The environment, as a result, transitions from a state to the next state and emits a reward. The agent goal is to maximize the expected cumulative reward. So in the general reinforcement learning problem, the next state depends on past actions and states. In particular, for instance, according to a Markov rule. But in the k-arm stochastic bandit, there is only one state. So as we see in the bandit, we have more structure. It's a more specific case, but this results in more specialized learning algorithms with faster convergence rates and with rigorous optimality guarantees. Here is a summary for the first part. In the first part, we studied the stochastic k-arm bandit problem, where arm rewards are samples from an unknown distribution. The arm rewards are independent of each other. For this problem, we show that any consistent policy incurs regret that grows at least logarithmically over time. Then we saw two policies, UCB and Thompson sampling, that achieves regret growing logarithmically over time. The UCB algorithm explores by being optimistic, and the Thompson sampling explores by sampling from the posterior. In the second part of the tutorial, I will talk about combinatorial bandit problems. I'll first formulate the problem and give examples from wireless communications. I'll formally describe the performance objective, which is the regret for combinatorial bandits. Then I will discuss a variant of the UCB algorithm for combinatorial bandits called combinatorial UCB, and I will show its regret bounds. Then I will talk about extensions and discussion. So in a combinatorial bandit problem, there are k base arms. Base arms yield random outcomes. The outcome vector from the base arms at each round is sampled from a fixed but unknown distribution f. We assume that the base arm outcomes lie in the unit interval. In this problem, there are superarms. A superarm is a collection of base arms. For instance, base arm 1, 3, and 5 is a superarm. And there is a set of feasible superarms. The set of feasible superarms is a subset of the power set of base arms. In this problem, the learner in each round selects a superarm, and the reward of a superarm depends on the outcomes of the base arms in the superarm. And I will start by assuming that the reward is the sum of the outcomes of the base arms in the superarm. This scenario is known as linear rewards. So in each round, the learner selects a superarm from the set of feasible superarms. It collects a reward for the selected superarm. This is called bandit feedback. And it observes the outcomes of the base arms in the selected superarm, which is called semi-bandit feedback. The goal of the learner is to maximize the expected cumulative reward over rounds. One example of combinatorial bandits is multi-user communication. Consider L users and K channels, where L is less than or equal to K. We assume that only one user can transmit on each channel. If more than one user transmit on the same channel at the same time, collision happens, so users obtain 0 rewards. In this case, base arms are user channel pairs. The base arm outcomes are the throughput that users can get from those channels when they transmit as the sole user of that channel. and the superarms are one-to-one matchings of users to channels. The reward of a superarm is the sum of the throughputs. In the figure, you see a scenario with 3 channels and 2 users. In this scenario, the green matching shows the optimal matching, which yields a sum reward of 1.7. And the red matching is a suboptimal matching, which yields a cumulative reward of 1.6. Another example is path selection. In this case, base arms are links between nodes. Superarms are paths from source to destination. Each superarm consists of a certain number of links. Base arm outcomes are link delays, and superarm loss is the total delay from source to destination. So given that the link delays are random, how can the learner choose a path in each round in order to minimize its sum of delays? So let's describe the regret. For that, let's define the expected outcome of a base arm as mu of A. And let's define the expected outcome vector or expectation vector as both mu. The optimal superarm is among the feasible superarms, the arm that maximizes the reward under mu. The regret of a policy is the difference between the cumulative reward obtained by always selecting the optimal superarm and the cumulative reward obtained by the superarm selected by the learner. And we know that maximizing the expected cumulative reward in a combinatorial bandit is equal to minimizing the regret. Since we are considering a combinatorial setting, even computation of the optimal superarm when the problem parameters are known is a difficult problem. For this, the learner resorts to offline optimization oracles. The oracle knows the feasible superarm set. It also knows the structure of the reward function. And given in a parameter vector theta that represents the expected base arm outcomes, the oracle returns the arm which maximizes the reward under the given parameter. It is known that many computationally efficient optimization oracles exist for practical combinatorial problems. For instance, in maximum weighted bipartite matching problem, Hungarian algorithm is an efficient algorithm, or in the shortest path problem, Dijkstra's algorithm is an efficient algorithm. Next, I will describe you the learning algorithm, combinatorial UCB. Similar to UCB algorithm from the previous part, the algorithm stores and updates cumulative rewards and play counts for each base arm. Initially, it selects superarms such that it initializes each base arm with one observation. Then, at each round, the algorithm calculates upper confidence bound indices for each base arm, which consists of sample mean plus exploration bonus. Now, these upper confidence bound indices are fed to optimization oracle, and the optimization oracle is going to return the superarm to be played S of t, which is the optimal superarm based on the UCB indices. Note that this could be different from the optimal superarm based on the true expected outcomes. Then the learner selects superarm ST. It observes the random reward from that superarm and also observes the outcomes of the base arms in the superarm. And it uses these outcomes to update the parameters. This theorem characterizes the gap-dependent regret bound for the CUCB algorithm. It basically says that the gap-dependent regret increases logarithmically over time. Moreover, it's proportional to k times L times 1 over delta, where k is the number of base arms, L is the maximum number of base arms in a superarm, and delta is the gap between the best and the second best superarm. There is also a gap-free regret bound. The CUCB algorithm achieves a gap-free regret bound of square root of k L T log T. And these bounds are near optimal. They're almost matching lower bounds for the combinatorial bandit problem. There are certain extensions to this problem. One extension is the case with nonlinear rewards. So in this case, the rewards are no longer linear in the base arm outcomes. However, we need certain structural assumptions in order to analyze the regret. Most of the times in this case, it is assumed that the expected reward of a superarm varies smoothly with the expected outcome vector of the base arms. For instance, this expected superarm reward can satisfy a Lipschitz continuity assumption, which tells that the difference between the expected rewards of superarm S under realizations mu and mu prime of the base arm parameters is a Lipschitz continuous function of the parameters that correspond to the base arms in S. There is another assumption that is usually made to analyze the regret in this problem. It is the monotonicity assumption, which basically tells that the expected rewards of the superarms are monotone in the expected base arm outcomes. With these assumptions, we can use the same algorithm, CUCB, but with different optimization oracles. We still give the optimization oracles UCB indices to get an estimated optimal superarm and then play it in each round. And the following theorem characterizes the regret for this more general case. So under Lipschitz continuity and monotonicity assumptions, it is known that the regret of CUCB grows like square root of T log T. The methods that I have described so far exploit correlations between superarms, knowing that superarms share base arms, but they do not explicitly exploit correlations between base arms. Next, I will talk about how to exploit correlations between base arms. For this setup, we assume that the base arm outcomes are samples from a Gaussian process with a known kernel, and we investigate the combinatorial version of the Gaussian process upper confidence bound algorithm. So the algorithm at each round computes the posterior mean and variance of the base arm outcomes, and it computes GP-UCB indices for the base arms, which are equal to the posterior mean plus a constant times the posterior standard deviation for each arm. The computation oracle is then fed with the GP-UCB indices, and it returns a superarm to select. This superarm is selected, and afterwards its reward is collected, and the outcomes of the base arms in the superarm are used to update the posterior distribution of mu. This model is able to learn from the correlations between base arms. So the regret bounds in this case depend on the maximum information that can be gained about the expected base arm outcomes within T rounds. Next, I will talk about how combinatorial UCB can be extended to work with approximation oracles. For many combinatorial problems of interest, there is no computationally feasible exact oracle. However, combinatorial UCB can work with alpha-beta approximation oracles as well. So an alpha-beta approximation oracle takes as input the expected base arm outcomes, and it outputs a superarm that achieves at least alpha fraction of the expected reward of the optimal superarm with probability at least beta. For many combinatorial problems of interest, computationally feasible alpha-beta approximation oracles exist. When using alpha-beta approximation oracles, we measure the regret with respect to the alpha beta fraction of the optimal. That is, the regret is defined as alpha beta times the expected total reward of the optimal superarm minus the expected total reward of the selections of the algorithm. Finally, I will also talk about a Thompson sampling-based algorithm called combinatorial Thompson sampling. I will explain how it works when the base arm rewards are Bernoulli. So the algorithm stores and updates success and failure counts for each base arm. At each round, it samples a parameter from the posterior of every base arm, and it queries the optimization oracle with posterior samples for the base arms. The oracle returns an optimal solution by assuming that the true parameters are equal to these posterior samples. Afterwards, the superarm is played, the reward is collected, and the observed base arm outcomes are used to update the posteriors of the base arms in the selected superarm. So when base arm outcomes are independent, it is known that combinatorial Thompson sampling achieves a gap-dependent regret that increases logarithmically over time. However, combinatorial Thompson sampling's regret bounds hold under the assumption that the computation oracle is an exact oracle. It's also known that for many combinatorial problems of interest, combinatorial Thompson sampling works well, but there are some problems it may not work well, especially in the bounds, regret bounds. There's a term that doesn't depend on time, but this term can grow exponentially with the number of base arms. Here is a scenario where we compare UCB-based algorithms with Thompson sampling in a combinatorial bandit with linear rewards. Here, there are 150 base arms. Each superarm consists of 10 base arms. And here we assume expected base arm outcomes are sampled from a GP. Here, combinatorial Thompson sampling is implemented using independent Gaussian posteriors for each base arm. And we see how the cumulative regret increases over rounds. So we see CUCB has the highest regret, followed by combinatorial Thompson sampling. And the lowest regret is achieved by combinatorial Gaussian process UCB. Well, this is due to the fact that in this problem, the base arm rewards are actually correlated, but the other algorithms, combinatorial Thompson sampling and UCB, do not use these correlations. But all these algorithms use correlations between the superarms, and their regret scales very well with the number of superarms. Here is a summary of this part. We introduced combinatorial bandits with semi-bandit feedback. We considered applications of combinatorial bandits, including centralized multi-user communication and path selection. We studied CUCB algorithm and showed that it achieved near-optimal gap-dependent and gap-free regrets. We studied extensions, including extensions to nonlinear superarm rewards, extension when the base arm rewards are correlated using Gaussian processes. We studied how to use approximation oracles in returning the superarms. And we also saw a Thompson sampling-based combinatorial learning algorithm. In the third part of the tutorial, I will talk about decentralized multi-user bandit problem. I will first formulate the problem, then talk about the centralized solution and regret. Then I will talk about the decentralized solution, and I will conclude with extensions and discussion. So in the decentralized multi-user bandit problem, there are L players, also known as users. There are K arms, also known as channels, and L is less than or equal to K. Users are synchronized. That means that they have the same clock. In each round, user N selects an arm. And if there's more than user on the channel selected by user N, a collision happens. When there's collision, colliding users get 0 reward. And there is a collision feedback, eta, which is 1 if there is no collision, and 0 if there is collision. So user N observes the collision feedback on the arm selected. As I said, colliding users get 0 reward. If there is no collision, then the user also observes a Bernoulli reward that comes from a Bernoulli distribution with an unknown parameter that depends on the user and the channel. For instance, this could represent packet success or failure due to other channel conditions. The parameters are the Bernoulli parameters for each user channel pair. These are assumed to be positive but unknown. In the decentralized setting, users do not observe others' actions and rewards. They only get to observe their actions and their own rewards and collision feedback on their selected channels. And the goal is to maximize the expected sum of total rewards, which is summed over all time slots and overall users. Next, I will talk about the centralized version of this problem. In the centralized version, each user must select, in other words, sit on a different channel to avoid collisions. But this problem turns out to be same as combinatorial bandit with linear rewards, where base arms are user channel pairs, super arms are user channel matchings. Feasible super arm set is the set of orthogonal matchings. The optimization oracle we can use is Hungarian algorithm. And the optimal superarm, represented by S star, is the arm that maximizes the expected sum of rewards. We assume that this optimal superarm is unique. Well, the regret is defined as the difference between cumulative reward of always selecting the optimal superarm and expected total reward of users employing their policy. Let's recall the combinatorial UCB algorithm from the previous part. We can use this for the centralized version of the problem. And we know that CUCB achieves logarithmic in T gap dependent and square root of T log T gap free regrets, which are near optimal. Next, I will talk about the decentralized solution and present key ideas. For the decentralized solution, assume that the time horizon T is known by all users. The question is, can we minimize the expected regret in the decentralized setting without any explicit communication? This is addressed by Bistris and Lessam. They propose an algorithm that have 3 phases. The first phase is exploration phase. In the exploration phase, each user tries to learn its own expected rewards. This phase lasts for TE rounds. The second phase is agreement phase. In this phase, users try to converge to the optimal superarm distributedly using a utility-based dynamics. This phase lasts for TG rounds. The third phase is exploitation phase. In this phase, each user selects the agreed arm. This phase lasts for the remainder of the rounds. So as you see from this figure, the users are synchronized, so they start each of these phases at the same time. Next, I will describe details of each phase. In the exploration phase, each user runs the following protocol independently of the other users. So each user stores and updates cumulative rewards and play counts for each base arm. In each round in the exploration phase, user N selects a channel uniformly from the channel set or arm set. It observes the collision feedback represented by eta. If there is no collision, the user collects the Bernoulli reward and uses it to update the cumulative reward and play count of the selected arm. If there's a collision, no update is done. At the end of the exploration phase, user returns for each arm the sample mean reward. The sample mean rewards are the estimated expected rewards from the arms of that user. Here is a lemma that bounds the exploration error probability. Let S star EXP be the estimated optimal allocation based on the estimated expected rewards at the end of the exploration phase. Then, probability that this estimated optimal allocation not equal to the true optimal allocation vanishes exponentially with the length of the exploration phase. This means that we can make this probability arbitrarily small by adjusting the length of the exploration phase, for instance, as a logarithmic function of the time horizon. Next, I will talk about the agreement phase. In this phase, users play an arm selection game using a utility-based dynamics, which is known as Game of Thrones. Here, each user have a unique arm in the optimal allocation called the throne for that user. The goal of this dynamics is to locate the throne. The utilities in this game depend on the estimated expected rewards that come from the exploration phase. So in each round, in the Game of Thrones or GOT phase, user N selects its arm based on the dynamics. It observes whether there is collision or not and collects reward, and it also records selections. At the end of the GOT phase, by looking at its selections, the user calculates a throne, A star N. We expect this throne to be equal to the arm that the user will select in the true optimal allocation. Next, I will talk about the details of the dynamics. So for user N, we have a state model. The user N keeps a baseline or preferred arm Bn. It also has a status, content, or discontent. And the present state of the user consists of baseline arm and status pair. Initially, users are content and their baseline arm is selected uniformly. Next, I will describe a status-based arm selection rule. According to this rule, a content user likely sticks with its baseline arm, which means that with a very high probability, it will select an arm equal to the baseline arm. But with a small probability, it will randomly select an arm. Here, epsilon and c are hyperparameters that define the rate of exploration. A discontent user, on the other hand, explores uniformly. Note that exploration here is different than exploration done for estimating the rewards. Exploration here is done for the purpose of discovering the optimal allocation in a distributed way. So utilities in this phase are defined as follows. A user's current utility is the product of the estimated expected reward of the selected arm that comes from the exploration phase and the collision indicator on the selected arm. So if the user observes a collision on the selected arm, the current utility will be equal to 0. Maximum utility of a user is defined as the maximum expected reward it could get as the sole user of any particular arm. Here is the state update rule. When a user is content, if its selected arm coincides with the baseline arm, and if the user receives a positive utility from the selected arm, its state doesn't change. If a user is content, if its selected arm differs from the baseline arm, or if the user observes a zero utility, which indicates a collision, the following transition happens. The user state, next state, will be the selected arm and content or discontent pair, with the probability of content being proportional to the utility that the user receives. If the utility is 0 with probability 1, the user will transition to a state with status discontent. The same transition rule happens when the state of the user is discontent. So the dynamics that I mentioned introduce a Markov chain on the joint state space of all the users. And under mild assumptions, and when the exploration length is long enough, this chain is ergodic. Its stationary distribution is pi. We know from the previous lemma that the estimated optimal allocation returned at the end of exploration phase coincides with the true optimal allocation. We call the true optimal allocation the true optimal state. And we can show that if hyperparameter epsilon is small enough, then the stationary probability of the true optimal state would be at least 1/2, which means that if the users play according to this dynamics for a long time, they will be playing the true optimal state majority of the time. This gives us an idea about the succession. So each user for each arm computes time spent being content on that arm during rounds in the GOT phase. And the thrown of user n is determined as the arm that is played the most of the time being content in the GOT phase. This lemma shows the error probability of the GOT phase. Let S star GOT be the superarm returned after GOT dynamics, which includes for each user the thrown of that user. Then probability that S star GOT not equal to S star at the end of exploration phase vanishes exponentially with the length of the GOT phase. Inside the exponential term, Tm in the denominator represents the mixing time of the induced Markov chain by the GOT dynamics. So if the mixing time is large, GOT phase length needs to be larger in order to offset that. Next, I will describe the final phase, exploitation. In the exploitation phase, each user always selects its thrown return at the end of the GOT phase. Here is the main result. If all users set their exploration and GOT phase lengths the same and logarithmically increasing over t, then the expected regret is bounded as a logarithmic function of time. So players or users in a distributed way can achieve order optimal logarithmic regret. Here's a sketch of the proof. We know that exploration and GOT error probabilities vanish when exploration and GOT phase lengths are large enough. So by setting them as logarithmic functions of time horizon, we can achieve a very high probability of the returned optimal allocation at the end of GOT phase matching with the true optimal allocation. So if this high probability event holds, we know that only regret comes from exploration and GOT phases. And their length is logarithmic in time, so the only contribution would be logarithmic in time regret. If this high probability event doesn't hold, the regret could be linear, but we know that this event will not hold with probability at most 1 over t, so the contribution to the expected regret coming from this event not holding is very small. Now let me talk about several extensions. One interesting extension is when the time horizon is not known beforehand. This case is solved by introducing an epoch-based structure where users run exploration, Game of Thrones and exploitation phases in epochs. And the length of these phases are adjusted based on the epoch so that near optimal regret can be achieved without the knowledge of time horizon. There are other important extensions, such as working with continuous rewards, working with Markovian rewards, or considering fairness issues. Another extension is considering ways to reduce the number of collisions happening in the exploration phase. Since the exploration phase is uniform, a lot of collisions could happen. And recently, orthogonal exploration techniques that reduce the number of collisions have been proposed. Another recent work considered an extension of this problem to the dynamic rate and channel adaptation setup. In this setup, each user in each round selects a channel and a transmission rate. And the expected rewards depend on both the selected channel and the selected rate. In the exploration phase, the proposed method used a technique called sequential halving orthogonal exploration. Here, the sequential halving algorithm is used to identify the optimal rate for each channel as fast as possible, while orthogonal exploration is used to reduce the number of collisions in the exploration phase. Now, the goal is to return for each user a throne, which will be a channel, but also the best rate on that channel. So in the agreement phase, GOT algorithm is run over channel and channel's estimated best rate pairs. And at the end of the GOT phase, for each user, a throne and throne's estimated best rate are returned. In the exploitation phase, these are selected by the users. It is shown that the regret scales well, both in the number of rates and the number of channels. Another interesting extension is when there is no collision sensing. In other words, when collision feedback is not present. So far, we considered the heterogeneous case, where each user can get a different reward from the same channel. For the no collision sensing case, we will focus on the homogeneous case, where channel C yields the same expected reward for all the users, and this holds for all channels. So for this homogeneous case, it is known that with collision feedback can be used for implicit communication, so that users can coordinate in order to achieve a good regret with a gap to centralize largely closed. So the regret they can achieve is as good as the centralized case, not just in terms of the time order, but also in terms of the constants that multiply the time order. In the no sensing case or no collision feedback case, the users do not know collision information. This creates a problem because a zero reward can come either from collision or natural random reward generation, and users cannot distinguish it. For instance, a communication failure can be a result of either other users transmitting on the same channel or instantaneous channel noise is very large. In this case, the regret gap between centralized and decentralized settings is large. This gap is closed in a recent work, and an algorithm based on implicit communication and error correction coding for Z-channel is proposed. So the main result from this is that the decentralized multi-arm bandit problem without collision feedback can asymptotically approach the performance of centralized multi-user bandit problem. Here, information theory and coding theory found a surprising application in the bandit problem. So I'd like to close this part by giving a summary. In this part, we studied the decentralized multi-user map. We mainly considered the case with heterogeneous rewards and collision feedback and synchronized users. We saw a distributed algorithm that has three phases: explore, GOT, and exploit, and show that it achieved logarithmic in T growth of regret, which is order optimal regret. We also studied several different extensions of the problem. And the final part, I would like to mention other bandit models. One other bandit model is contextual bandit. In a contextual bandit, in each round, the learner observes a context, X of phi. It will select an arm after observing a context, and it collects a reward, which is a noisy reward that is sampled from the reward distribution of that arm, which is also parameterized by the context. Examples of context in wireless communications include user position, base station position, partial channel state information, or others. Here, the challenge is again how to maximize the expected cumulative reward. Now, the problem is that the expected rewards depend not only on the arm, but also on the context, and this is unknown. Learning is hard, especially when the set of contexts is very large. Therefore, we need to find mechanisms that can efficiently explore and exploit for each context. So to learn fast, we usually need additional structure on the problem. There are two famous ways to impose additional structure. The first one is contextual linear bandit. And the contextual linear bandit, the expected reward of arm A given context X is assumed to be a linear function of an unknown parameter theta star and a feature map that maps action and context to a space with the same dimension as the unknown parameter vector. Another variant is Lipschitz contextual bandit. In the Lipschitz contextual bandit, the expected reward is assumed to be smoothly varying with the context. There are several extensions to the contextual bandit problem. One of them is contextual bandits in high dimensions. In this extension, it is assumed that the context set can be high dimensional, but the reward of each arm only depends on a small subset of relevant dimensions. A subset of relevant dimensions for each arm is unknown, so there's sparsity structure in the problem. It is known that traditional contextual bandit algorithms suffer from curse of dimensionality. However, using sparsity can result in faster learning and regret that scales only with the number of relevant dimensions. Another extension is studying cooperation in contextual bandits. This is a cooperative multi-user setting where users have different sets of arms. A user can select its own arm in each round or pay other users to select an arm for itself. So here, users can accumulate higher rewards by cooperating with each other instead of just playing their own arms. Finally, I'd like to close this part by pointing some of these references. So here is a list of references for K-arm bandit problems. Here is a list of references for combinatorial bandits, decentralized multi-user bandits, and contextual bandits. Of course, there are many more interesting papers, but I hope that
Hello, I am Mihaela van der Schaar, and today I would like to tell you how we can formalize and solve a variety of wireless communication problems using reinforcement learning. While today, in the era of machine learning, it may sound obvious that we can formalize and solve wireless communication problems using machine learning, and more specifically, reinforcement learning, it was not so when I started as an assistant professor in early 2000. At the time, wireless communication systems were not truly optimized and solved using machine learning methods. So I'm going to take you today into a journey through my own research from early 2000 up to around a few years back, where we have started to formalize rigorously and solve wireless communication problems as decision-making under uncertainty and solve them using elegant reinforcement learning solutions. Now, in the era of deep learning, we have a new opportunity to revisit some of the work and enhance it using deep learning methods. I have started to formalize wireless communication in the single agent setting as a cross-layer optimization problem, a multi-objective optimization problem. This will represent the beginning part of this tutorial. Then I'm going to move to the dynamic setting. Subsequently, I will move to the multi-agent wireless communication setting, where I'm going to first discuss a scenario in which multiple users are sharing spectrum and are compliant with the protocols prescribed to them. I'm going then to move to the strategic setting where wireless users are competing for resources. I'm going to then go beyond wireless communication and talk about how these ideas can be applied in social networks, content caching, etc. Let me now start with a single agent wireless communication setting. So why is wireless communication a problem that requires machine learning? We know that different layers of the protocol stack have different algorithms associated with them. We have multiple algorithms from which we can select, and these algorithms have often their own hyperparameters that need to be optimized for efficient transmission. For instance, at the MAC layer, we can decide the retransmission scheme that can be used by a wireless transceiver in order to maximize their short-term or long-term throughput and or delay. An important question that we studied in early 2000 is, can protocols alone provide optimal solutions for wireless communications? And the answer is no, because protocols are simply a set of standards defining message formats and exchange rules across the different layers of the protocol stack and between transceivers. But they are not telling us how to optimally select the various algorithms, parameters, and how to create optimizations across the different layers of the protocol stack in order to maximize throughput, minimize power, fulfill delay constraints, etc. So what we need is a cross-layer design and optimization solution in order to optimize the performance of a transceiver. This is essential because it leads to improved performance over wireless networks it provides guidelines for designing and optimizing interlayer message exchange. So for instance, the middleware of transceivers can be optimized in this way. And it also provides valuable insights on how to design next generation wireless communications and networking algorithms and protocols at all the various layers. So I have formalized in early 2000 wireless transmission as a cross-layer optimization problem. So what we need to optimize are a variety of algorithms and parameters at the different layers of the protocol stack. And of course, the degree of adaptability is limited by the specific protocol adopted at that particular layer. What we have as an input is the multimedia characteristics, or if you use another application, the application layer characteristics and requirements, as well as the wireless communication characteristics. What we need then to output is the optimal cross-layer strategy, which selects at the different layers of the protocol stack the best algorithms and associated hyperparameters. This is an optimization problem that we need to solve, and the utility associated with this optimization problem can be defined by the user. It can be the video quality, it could be the throughput, it could be a trade-off between throughput and power considerations. It could also involve system-wide network optimization. So we formalize this as an optimization problem with the utility defined by the user, and where given the input, we are going to determine the optimal algorithms and parameters to be selected across the different layers of the protocol stack. This optimization problem has also various constraints. These constraints could be power constraints imposed by the different protocol, system constraints in terms of fairness constraints, delay constraints, etc. So we have, for the first time in early 2000, formalized the cross-layer optimization problem as a cross-layer optimization, a multi-objective optimization, which selects the different parameters at the different layers of the protocol stack. However, there are challenges associated with solving this cross-layer optimization. And we have outlined an entire research agenda associated with this field in the middle of 2000. First is the fact that we have time-varying inputs. The application layer may have different characteristics, different traffic considerations over time, as well as different requirements. Wireless channels are also fluctuating over time. And we have also time-varying constraints. For instance, if we are transmitting video over different wireless communication scenarios, we would have delay constraints at the application layer in order to have effective video communication. Other constraints could be due to multi-user constraints, and all of these are time varying. So this optimization problem that I described previously needs to be solved repeatedly, again and again, as the input characteristics or constraints are changing over time. And this is a complex optimization problem. It is a multi-objective optimization problem that is expensive to solve, and it will lead to either very high cost for transceivers or suboptimal performance. So how can we deal with this challenge? An elegant way to address this challenge was provided by us again in the middle of 2000, where we formalized this problem as a machine learning problem. So how did we turn an optimization problem into a machine learning problem? We know that depending on the input characteristics and the constraints, different types of cross-layer optimization solutions are going to emerge. So offline, at training time, we can solve multiple cross-layer optimization problems under different inputs and constraints and for different types of utilities. This represents the training set that is provided to the transceiver and which has as label the cross-layer strategy. So this is multi-label classification. And this particular classification problem can then be used to train supervised learning problems, to supervised learning solutions. For instance, in this particular paper, we formalized it using support vector machines, but other supervised learning methods can be used. So we can then, at runtime, just look at the current input characteristics as well as constraints and predict what would be the optimal cross-layer strategy to be used by this transceiver. So in this way, we have elegantly solved the iterative optimization problem, and we have turned it into a machine learning problem where at runtime, we just need to make a prediction as to what would be the best cross-layer strategy given the unique input characteristics. Nowadays, in the era of deep learning, I think that this work can be significantly improved and enhanced by using sophisticated machine learning methods that go beyond the support vector machines that we have used in this early work. But a limitation of this is that if it is to solve this problem using supervised learning, we are only optimizing the protocol stack based on instantaneous utilities and constraints. Instead, we can go one step further and model the problem of wireless transmission over a time-varying channel as learning and decision-making under uncertainty. And this is, of course, reinforcement learning. We have formalized this problem as a reinforcement learning problem in the early 2000s, but the most rigorous solution for that we have provided in 2007. And I'm going to describe some of these ingredients next. So discrete time Markov decision processes, or for short MDPs, are extensions of Markov chains where we have actions and rewards associated with them. So we have S, which is a finite set of states. We have actions which are going to be selected in the different states. And we have utilities or cost functions, C, which are going to be associated with taking a particular action A in a particular state S. We also have a dynamic environment where the probabilities of changing to a new state, given the fact that we are in a current state S and choose an action A, are going to be synthesized by this transition probability function P. We are optimizing not only myopically, like in the previous example, the utility or the cost. This time we are going to optimize a long-term utility function. And because of that, we need to discount the future. So we are going to also select a discount factor gamma. This discount factor gamma can be in wireless communication settings either set up as the probability of discontinuing the transceiver in the next time slot, or can be based on the time varying characteristics and how non-stationary the current dynamics of the environment are. Let me just consider here the simplest scenario where I just have the application layer and the physical layer interacting with each other. And indeed, we have formalized and solved this in early 2000. So at the application layer, we have a state which is the buffer fullness, how many packets are in that particular buffer at that particular moment in time. And as actions, we have packet scheduling, so how to schedule the different packets and when to transmit them, and potentially in what order to transmit them, as well as if we have real-time encoding, for instance, for video conferencing, how to exactly encode that particular packet. For instance, how much dependencies we should have between the different packets, etc. The state transition is the buffer transition, how we can move from the current buffer state to a next buffer state, depending on, for instance, the packet scheduling or source coding strategy. The reward or the cost could be defined in terms of distortion reduction, or if we have cost distortion, or video quality, if that is the preferred metric. At the physical layer, we have as the state the signal-to-noise ratio, and as actions the modulation and power associated with the transmission. And the state transition is the signal-to-noise ratio transition. The cost is the consumed power. So this is an example of how we can map a Markov decision process, how we can solve this problem and map them into Markov decision problems. Like in all reinforcement learning problems, we do not know the state transitions and we do not know the rewards. They need to be learned online. So this is why this is not a Markov decision problem, which can be solved using dynamic programming solutions, but rather a reinforcement learning problem due to the uncertainties associated with state transitions and reward. It is important to note that, like in the previous case, in the supervised learning setting, where we can use support vector machines to solve the cross-layer optimization problem, in this particular setting, because we formalize it as a reinforcement learning problem, we are going to consider not only the immediate cost and reward, but also the impact of actions into future rewards. So we are going to optimize a long-term reward. I am having here a pictorial example of how this reinforcement learning problem that I described in the previous slide can be formalized into reinforcement learning problem. And again, we have packet buffer states, channel states. We often may model the channel states using finite state Markov chains, but we can also adopt the model-free approach. We have the system states, which contain information about both the packet buffer state and the channel state. So we have here a vector state. We have scheduling actions, which determine what packets to transmit and when. And we also have arrival probabilities from the application layer. And one particular assumption we could make, but we don't need to make, is that these arrivals are IID. Note that we have uncertainties, both in terms of channel states, as well as packet arrivals. And this is why, again, this needs to be formalized as a reinforcement learning problem rather than simply solved using dynamic programming. Again, the buffer state can be modeled as a controlled Markov chain. And in order to determine what will be the optimal action, the optimal scheduling strategy, we will need to solve this using reinforcement learning. And the utility that we would like to optimize is a cost in this case, which is a weighted sum of two terms. The first term is the transmission power to transmit Y packets given the current channel state age, and a buffer cost that is penalizing large queue backlogs and overflows. This can also be seen as a surrogate of the delay. So we have here this weighted cost, which contains again the holding cost and the expected overflow cost. Lambda is the trade-off of the transmission cost and the buffer cost. And again, we need to solve this optimization problem under uncertainty because PL, it is not known. So we have the states, we have the actions, we have this cost, this weighted cost, we have the transition probabilities, which are influenced by the current state as well as the action chosen, and as I mentioned before, the discount factor. And what we are trying to optimize is, as I mentioned before, the actions or the policies to choose, which are, in this case, we are going to assume a deterministic policy, but we could also have probabilistic policies. But for the sake of simplicity, I'm going to assume here just deterministic policies, and optimize the long-term reward, which is this value function V, which is depending on the chosen policy pi. And it is this value function which represents the long-term reward that needs to be optimized. In the case this is a cost, it needs to be minimized. in the case this is a utility, it needs to be maximized. So this is the expected value function, which we are trying to optimize, the long-term utility function that we are trying to optimize. And of course, this value function can be expressed recursively using the transition probability function as indicated at the bottom of the slide. And this can be, of course, elegantly solved, as we know from dynamic programming, using Bellman equations. So we need to determine the policy pi that leads to the smallest transmission cost over time. As I mentioned, V pi and hence V star satisfies the Bellman equation. And if this was just a Markov decision problem and the probabilities, transitions, and the cost were known, this could be solved using dynamic programming, either value iterations or policy iteration. But in this case, we do not know the state transitions and the costs, so we need to learn them. And one elegant way to solve that is by considering not the value function, but rather the Q function, and determine the action value function, the optimal action value function, and the optimal policy pi star associated with this. And we can solve them, as is well known, using model-free approaches, for instance, using Q-learning. We can start by initializing the Q values, and this initialization could be either done by putting these Q values to 0, or rather with some setting, some Q values that were determined in a previous usage of this transceiver. So we do not need to start from scratch, because it is our belief that current transmission scenarios may be similar to previous transmission scenarios. And by smartly initializing these values, we will have faster convergence. And then we take actions by using a trade-off between exploration and exploitation. So with probability epsilon, we are going to exploit. We are going to select the action that will minimize the Q function at the current moment in time, given the fact that we are in state ST. And with probability 1 minus epsilon, we are going to select randomly another action. Then we are going to observe what has happened in this particular case. We are going to observe the cost associated with this action, as well as the state transition. So the new state at which we have landed as t plus 1. And in this way, we are going to be able to learn from this experience. And in the last step, we are going to update the action value function on the basis of what we have learned. And we are going to use a parameter, a learning rate alpha t, which is going to update the current value of the Q function in this particular state ST, given the fact that it chose action AT. And depending on the learning rate, we may update the Q function based on the current experience or past experience QT with a higher or lower weight. However, if it is to use such Q learning to solve wireless communication problems, this has limitations. As you can see here, first, it updates only one state action pair in each step. So the updates are slow. The transceivers are going to learn in a very slow pace. Also, this assumes no a priori information about states, state transitions, or cost. And unlike in other problems in which reinforcement learning is used, such as, for instance, self-driving cars or other problems where reinforcement robotics, in wireless communication, we have very good models. We do know a lot about how to model wireless communication settings and wireless communication channels, network layer, or for that matter, application layer, also using, for instance, hierarchical Markov models. Such models are not used to empower the reinforcement learning framework if it is for us to use vanilla Q learning. So there is an opportunity to use a priori information from wireless communication and models used in wireless communication to improve the speed of learning of reinforcement learning and go beyond Q learning. And if it is to do so, we can limit the number of explorations and improve performance. So what we have advocated early on in 2000 was to navigate carefully this space of reinforcement learning, moving from model-free approaches such as Q-learning, which are very elegant but very slow and lead to a poor performance when used for wireless communication, optimization, and learning. So they have low complexity, but very slow convergence and poor quality, and move towards model-based approaches, which have a much faster convergence, but potentially may have a higher complexity. And this is work that we have pursued with a variety of former PhD students, inclusively Fang Wen Fu and Nick Mastronarde. And this is a slide that I got from Nick. So in a variety of papers, we have enhanced Q-learning for wireless communication by introducing first the idea of post-decision state. And due to that, we are able to update the Q function for multiple entries of the state action pair. So what you see here in this figure is that the fact that Q-learning updates the state action pair just once for the current state and the current action. However, if we use this concept that we introduced with Fang Wen Fu for post-decision state, we are able to accelerate learning and improve sample complexity by making multiple updates at the current moment in time. So it was not only the current state action pair, but also several state action pairs associated with it. So we can infer the Q function associated with these other settings, even though we have not observed them. Then in a subsequent work together with Nick Mastronarde, we have introduced virtual experience for post-decision state, and that enable us to also come up with approximations of the Q value function for all the state action pairs, even though we have observed just one action pair. Also, you can enhance these works now in the era of deep reinforcement learning by using deep reinforcement learning techniques. So this can still represent new improvements. Now, I have described how we can use reinforcement learning to model wireless transmission problems as decision and learning under uncertainty. But the reality is that the problem is complicated. We can entangle all these different decisions and actions at the different layers of the protocol stack together and solve one humongous reinforcement learning problem. Indeed, in some of the work that we have done so, both for packet losses and retransmissions at the MAC layer. Then in subsequent work, we have looked at dynamic power management and more recently at energy harvesting. But the challenge associated with this is that if it is for us to formalize this as centralized reinforcement learning problems, they are going to be complex. And possibly surprisingly, these centralized solutions are often going to also be suboptimal. So we are going to move to a decentralized approach, which will result in optimal solutions. So we have different layers of the protocol stack. I'm just highlighting here 3 layers, but the reality is that all the layers of the protocol stack can be involved. And every layer faces its own dynamics and has its own actions it needs to select. Note that if it is for us to solve this problem across the different layers of the protocol stack and consider all the states at all the different layers of the protocol stack together and all the actions, we will have an intractable, very high and complex Markov decision problem and reinforcement learning problem, which will suffer from the curse of dimensionality. It is well known that we have no way of learning effectively from a limited number of samples as required in wireless communication if we have this complex state action setting. Also, note that different dynamics at different layers are driven by different characteristics. So the physical layer is driven by the channel characteristics and interference, while the source characteristics are driven by a totally different force operating at very different time scales. So if it is to entangle everything together and solve it as a centralized approach, this will be intractable, as discussed in this paper in 2009. So we can formalize and try to solve that, but this would be very complex. So instead, what we need to do is we need to think differently. Let us first highlight the challenges. So we need to solve a decision-making under uncertainty, a reinforcement learning problem, but where the different layers across the protocol stack have their own states and actions, and hence the decision-making is coupled. We have environmental dynamics which are different and at different timescales across the different layers. The algorithms that we use at the different layers of the protocol stack, and hence the actions, are also operating at multiple timescales and granularities. And an important challenge is really, if it is for us to decentralize this Markov decision problem and reinforcement learning problem, how to decentralize it? What type of information exchange we need across the different layers, and how to optimize this effectively across time, and how to do that in a way in which is remaining protocol compliant, because the different layers of the protocol stack are requiring different agreements between different entities, but also potentially different companies, because in a transceiver, we have multiple companies implementing different layers of the protocol stack potentially, and hence they need to agree with each other how to exchange information in order not to violate the OSI stack and optimize the performance of this transceiver. There are also other challenges besides the fact that we do not want to violate the current layer architecture of the protocol stack. We also need to make aware the decision maker, if it is to formalize this as a centralized problem, of all the possible strategy combinations and dynamics at the different layers. And this may be very ineffective and also may violate intellectual property considerations, because different layers may not want to communicate this information to another layer of a competitor. Also, the problem still remains that we want to solve not a static optimization problem or a static learning problem, but rather a dynamic problem where we optimize the long-term utility, the value function and the Q function. So how to do that? How can we decentralize this reinforcement learning problem? How can we turn the centralized reinforcement learning problem into a decentralized reinforcement learning problem? And how do we do that effectively? And what information should the lower layer communicate to the higher layer, and conversely, the higher layers to the lower layers? We have done that, this type of distributed, decentralized reinforcement learning approach that respects the OSI stack in this particular 2009 work. And we have modeled the different layers of the protocol stack as multiple agents making decisions on behalf of their layer, given their own dynamics, but which are cooperative agents because they are jointly optimizing the utility function of the transceiver in the long term. But for that, we needed to invent new reinforcement learning methods, new decentralized reinforcement learning methods. I believe that the key ideas that we have developed then are still very pertinent today and can be used in a variety of environments and settings. So let me start by reminding you that we started with a centralized Markov decision process where all the different states and all the different actions were entangled together. And we try to determine the optimal policy to maximize some type of long-term reward. And what we have as our operator is a centralized dynamic programming operator. And we are trying to solve that using reinforcement learning. If it is to decentralize this dynamic programming operator, we have several insights. We need to come up with decentralization solutions for reinforcement learning that do not break the OSI stack, and are aware that every layer is providing to the layers above quality of service, and receives from the layer below quality of service. So a lower layer is going to provide the feasible quality of service set to the higher layer, from which the higher layer can select and communicate to the lower layer what particular operation point is desired. If indeed we are able to do so, we are respecting the layer nature of the protocol stack, where the key ingredient of the different layers of the protocol stack is providing quality of service to the layers above. So the key insight we can get from this philosophy of the OSI layer is that the decentralization of the reinforcement learning solution needs to be in terms of quality of service. On one hand, the provision or feasibility of quality of service that the lower layer provides to the higher layer, and subsequently, the higher layer needs to select the requirements it has in terms of quality of service and select the desired quality of service point from the feasible solution. So we can decentralize the centralized DP operator into a layer DP operator, which will be used for reinforcement learning as follows. So we have different layers of the protocol stack highlighted here. S1 is, for instance, the physical layer, and SL can be the application layer. And we have any number of other layers in between, denoted here as SL. And every layer is going to exchange with the layers above information about the quality of service it can provide. It can do so through what we call internal actions. So it is these internal actions that are going to provide the instantaneous quality of service that is feasible by the layer below to the layer above. Then the higher layers are going to determine external actions, which are going to be the downward messages, which are going to communicate to the lower layers the desired operation point, the desired quality of service selected by the higher layer in order to maximize its long-term utility, which will determine what quality of service is required from the feasible set by the lower layers. This is highlighted also here. So as I mentioned, we have on one hand external actions, which are the action performed to determine the state transition in order to obtain and maximize future rewards. And we also have internal actions, where which are the actions performed by jointly determining how many packets, for instance, can be successfully delivered to the destination. So this is the quality of service provided by the lower layers. So as I shown in here, we can now decentralize the cross-layer optimization and reinforcement learning problem using this dynamic programming operator. So now the utility function can be decomposed into internal costs and external costs at the different layers of the protocol stack. We have quality of service that is provided by a particular layer, L, to the layers above. So for instance, layer 1, the physical layer, is highlighted here in red. And what you see is these dots are the different quality of service points that are provided by this particular layer to the higher layer. This quality of service is determined in terms of packet loss probability, transmission time per packet, and transmission cost per packet. And this is a multi-objective information. And we have a Pareto frontier associated with this different quality of service or reward associated with the different selections of actions. It is this Pareto frontier, which we call quality of service frontier, which is communicating to the higher layer. So it is this quality of service frontier that represents the feasible set of operating points for the layers below. Note that there is no point in communicating points that are suboptimal and do not lie on the QoS frontier, because they will never be selected by the higher layer because they do not optimize performance. So it is this instantaneous quality of service information that's provided by the lower layers to the higher layers. And then the higher layers are going to determine the value function and the Q function associated with these different QoS frontiers and select the one that is going to lead to the best value function or Q function. The centralized DP operator is now going to be decentralized by this procedure, in which we are on one hand coming up with upward messages that are providing information about the quality of service provided by the layers below. And then the higher layers are going to select the operating point they would like by providing downwards messages which select the operating point. And this is determined on the basis of the value function at that layer. So this is decentralizing the dynamic programming operator and resulting in a layer dynamic programming operator, which can be solved effectively at every layer of the protocol stack, independently of the optimization of the other layer, but based on information that's provided by the higher layers in terms of value function and lower layers in terms of quality of service feasibility. This provides a very elegant solution for decentralized reinforcement learning, cooperative decentralized reinforcement learning using such a layer dynamic programming operator. And this layered reinforcement learning solution framework enables us to keep the layered architecture unaffected. We can upgrade protocols or change a particular layer without affecting other layers. So if you want to upgrade a particular layer and introduce new actions or improved algorithms, we can do so without changing the dynamic programming and reinforcement learning solution at another layer. So this leads also into minimal message exchange between the layers and improve significant performance improvements as opposed to ad hoc layer-centric optimization. So this provides a beautiful multi-agent decentralized optimization solution. In subsequent work that followed this work, we have looked also at a variety of other problems, inclusively transmission of delay-sensitive multimedia, like for instance for video conferencing, where we need to fulfill not only throughput considerations or delay considerations, but true real-time constraints. And hence, in this case, the states and state transitions at the application layer are even more sophisticated than in the previous example, because we have different packet dependencies and delays, and this leads to a more sophisticated state definition, as well as more sophisticated environmental dynamics, which require new and enhanced solutions for cross-layer optimization for delay-sensitive applications. You can see in this work that, for instance, we formalize these problems and solve them elegantly using by formalizing them as optimal stopping problems. Other work that formalizes wireless communication problems, transmission over wireless communication settings as reinforcement learning, but using effective model-based approaches can be found in this work. Here we use queuing approaches to model the state and state transitions at the higher layers. Let me now move from this single agent wireless communication setting into the multi-agent wireless communication scenario. I'm going to start with the compliant user scenario and move to the strategic user scenario. So if it is for us to transmit information over a wireless spectrum, we know that the wireless spectrum is shared across multiple users. So actions and decisions that are selected by one layer are going to influence not only the utility of the current transceiver, but also the utility of other transceivers. So this turns from a single agent learning problem into a multi-agent learning problem. And indeed, in 2000s, we have formalized and solved that as a multi-user learning problem. So we formalized the interference management problem in wireless communication, the power control games, as multi-agent learning problem. And we show that unlike water filling algorithms that were popular for interference management, which converge to ineffective Nash equilibria, we can do a lot better by allowing agents to learn, for instance, by building conjectures about other stations, and in this way play more effective equilibria. And we use different types of multi-agent learning approaches that are inspired. Some of them are bio-inspired, some are just using the characteristics of the wireless protocols to learn. And in this relatively simple but very effective multi-agent learning solution, we show the importance of multi-agent learning such that users that are aiming to maximize the sum of utilities of the across a wireless network are able to optimize their transmissions together. Note that in this setting, we are considering compliant users, which are going to be eager to optimize the sum of utilities. We have also solved that not only at the physical layer, like in the previous slide, but also at the MAC layer. And what is interesting here is that we can significantly improve on top of CSMA, CA protocols, so current collision avoidance protocols, by using learning. So we can learn different stations, different wireless transceivers can learn based on the collisions they observe, how to coordinate and when they should transmit. And this represents another type of learning, a very powerful learning, where on the basis of the different information that's fed back to the transceiver about the collisions, the stations can learn to effectively use the spectrum, and they can actually achieve perfect coordination. So they can learn to utilize every slot, and they can do so with minimal feedback and no explicit communication. This represents really very advanced but very nice multi-agent learning solutions that can achieve significant performance improvements as opposed to current communication protocols, which are learning very naively based on these backup strategies, which are very ineffective and leave a lot of wireless spectrum unused. Please take a look. Then in subsequent work with Yuanzhang Xiao in successive papers, we look at how we can minimize the energy that is used in wireless communication networks. And for that, we move from a current Markov decision process setting to a non-stationary policy setting. So for that, I'm going to start by introducing some taxonomy for spectrum sharing policies. We are moving from the static sharing policies, where the assumption is that the wireless characteristics and transceiver needs are not changing over time, into a dynamic sharing policy, where the requirements and opportunities for transmission are changing and dynamic over time. And in this case, if we do a dynamic allocation of spectrum, so again, I'm talking here no longer about the single transceiver, but rather multiple transceivers sharing spectrum. For instance, in a cognitive radio scenario, or for that matter, any wireless communication scenario, if you do dynamic spectrum allocation, this will be a lot more effective. However, most of the existing works at the time and even today are using stationary solutions, such as Markov decision processes, and use reinforcement learning. What we show in here is that by moving to non-stationary approaches for dynamic spectrum sharing, we can achieve significant performance improvement. And this is work that I have done together with my former student, Yuanzhang Xiao. Stationary policies have the action depending only on the current state, while non-stationary policies, the action depends on the history as well as the current state. And most existing works are stationary, and they model the decision problem using single user Markov decision processes. And indeed, if I have a single user Markov decision process, then indeed stationary policies are optimal. But if we want to maximize the sum utilities for transmission over the spectrum by the multiple transceivers, this is a multi-user Markov decision process. And then restricting our attention to stationary policies is suboptimal. And it is indeed well known that optimal resource sharing policies should be non-stationary, because the centralized users have conflicting objectives and have coupled constraints. Let me illustrate that in this example. So for instance, we have here two transceivers that have a particular noise power at both transceivers, as shown in here, at 5 milliwatts. And both users discount the throughput and energy consumption through this discount factor delta. And they have minimum average throughput requirements as shown in here. And let us assume that the channel gains are fixed and the goal is to minimize the energy. The state is the channel condition and the action are the transmission power levels. And a stationary policy where both users are transmitted at fixed power levels simultaneously are going to lead to this energy consumption for the two users. Then let us see what a simple non-stationary policy can achieve. So I'm going to start by describing a simple non-stationary policy, which is an alternative round-robin policy like TDMA. And the actions are time dependent. And what you can see that if we use this simple non-stationary policy, already we can improve the energy consumption for the two users as opposed to the previous stationary case. So this is better than the stationary policy. So can we do even better? Well, we can modify the round-robin TDMA policy as follows and allow the first transceiver to transmit more often. In that case, the energy consumption is improved even further. So this leads to an even better performance. And the reality is that finding the best cycle is really complicated. It's combinatorial. So what we do is we develop optimal non-stationary policies. And we actually show that the optimal policies are not cyclic. But the good news is that we can construct simple, intuitive, and general algorithms to build such policies. And this leads to significant improvements. We are moving here from a multi-user Markov decision process into a non-stationary algorithm, set of algorithms for decentralized transmission. I invite you to take a look at my work together with Yuazhang Xiao. We are describing a very elegant solution for long-term multi-user optimization. And we formalize this as repeated stochastic games and show significant performance improvement as opposed to multi-user Markov decision processes and multi-user reinforcement learning. And indeed, you can see here that as opposed to stationary policies or round-robin policies, such non-stationary policies can lead to significant performance improvement in terms of energy saving and number of stations that can be admitted. And as the number of stations increases, the performance improvements are truly significant. Let me now move one step further and move from multi-user scenarios where the transceivers are benevolent and they are learning and making decisions in order to maximize in a cooperative fashion the sum utility, into a setting where the agents, the transceivers, are strategic and they are negotiating for resources into a market-based resource management setting. And in a set of various papers in 2000, we have showed that we can use either mechanism design, pricing strategies, or auction strategies of all sorts to decentralize and allow stations to compete for resources based on their requirements in the strategic setting, or by making coalitions, or by using bargaining theory. The work on mechanism design is with my former student Fangben Fu. The work on coalition theory is with my former student Hyung-Kwon Park, and bargaining theory also with my former student Hyung-Kwon Park. Let me just briefly highlight the work with Fangben Fu, where we formalize this problem of multi-agent transceiver interaction that are strategic. we have the wireless spectrum, which is now no longer shared cooperatively, but rather the central spectrum moderator, which may be the base station or other type of policy manager, is going to provide spectrum for use to wireless transceivers, which engage into a strategic game to determine when they would like to pay for spectrum, given their valuation at the current moment in time for this spectrum. This valuation of the current moment in time for spectrum and decision to whether they should acquire spectrum at the current moment in time can be determined as a reinforcement learning problem, but with strategic constraints. So we are now having reinforcement learning with considerations of costs associated with transmission. So this is a multi-user stochastic game solved repetitively by wireless users using reinforcement learning solution. You hear a lot nowadays about multi-agent strategic learning, multi-agent reinforcement learning, but this type of work exists for many years. As you can see in our own work back in 2000, we have done a lot of work on multi-agent strategic learning, which is still pertinent and represents state-of-the-art today. So you see here, for instance, in this work with Fang Wen Fu, we show how different stations can engage using reinforcement learning into the strategic game, and they determine whether they are willing to pay for resources at the current moment in time, given their expected valuation for resources, and also the expected opportunities to acquire spectrum in the future. So they consider and make predictions and valuation of resources over time into the future. And this valuation is dependent on both their predicted resource needs over time, based on the experienced wireless communication setting, as well as application layer demands. And also they build models about the need for resources of their competing transceivers. More works in this area came in subsequent settings, where we show that if different transceivers have different strategies, for playing this stochastic game using reinforcement learning, they may achieve a better or worse performance. So we show the value of learning and the value of reinforcement learning in engaging in these competitive multi-user wireless games. We also have moved from the single agent setting to a multi-hop setting. So in this setting, we are not only solving an optimization problem, a reinforcement learning problem in one hop, but rather across different hops of a multi-hop wireless network, for instance, a mesh network. Also, this is solved subsequently in subsequent work as a multi-agent reinforcement learning, where different games and different interactions are played across the different hops. So for instance, a particular end-to-end transceiver trying to transmit across the different hops and making decisions across the different hops and reinforcement learning decisions across the different hops will need to not only consider the local information and the local game and interaction at one hop, but also how these decisions are going to influence the long-term, but also across space interactions with other transceivers they may encounter at different hops. So this is a beautiful multi-agent reinforcement learning played not only across the different layers of the protocol stack and not only across the different agents, but also across the different hops. And hence there are multiple interactions that need to be solved in a decentralized way across the different hops. This still represents state-of-the-art solutions in online learning using reinforcement learning in queuing theory in autonomic multi-hop wireless transmission. Let me now move beyond wireless communication and talk a little bit about how these reinforcement learning, multi-agent learning solutions can play a role at other layers of the protocol stack, in social networks as well as content caching. For instance, in subsequent work with former students Jie Xu, Yanis Andreopoulos, and Yuazhang Xiao, we show how in the Internet of Things setting, we are able to formalize these problems as reinforcement learning problems and determine how to schedule information and how to interact across smart devices. And we show the role of reinforcement learning and non-stationary policy allocations to achieve optimal performance. Another scenario that we have investigated is the use of distributed online exchanges where different agents negotiate with each other resources. And we have started by first determining an entire theory of using fiat money, where we are now building an entire economy of exchanges of resources using fiat money. The theoretical foundations were published in economic theory together with my former student Jie Xu and my collaborator William Zame. And then we use this theory or fiat money in subsequent works to design autonomic wireless relay networks in which agents are learning and negotiating resources using tokens in multi-hop networks, in interference management, together with my former student Zong Shen and Jie Xu, as well as device-to-device communication together with Nigma Stronarde, Jie Xu, as well as the students of Nigma Stronarde. In another set of works together with collaborators, we have looked at, again, ideas from reinforcement learning for trend-aware video caching, as well as context-aware proactive content caching in wireless networks, where depending on the different contexts, both in terms of wireless communication, but also the desirability of different content, we can come up with different types of caching strategies that are more effective. Please take a look. Again, the same ideas of reinforcement learning play a very important role to make decisions as to how to cache content and how to distribute content across diverse distributed network. We also use the same ideas to forecast popularities of content in social media. So this can go beyond just physical layer considerations and maybe content delivery networks considerations, but also look at a variety of applications, dynamic applications such as social media. Then moving one step further, we also had looked at learning in a variety of social networks where the different transceivers are forming links based on the interest they have to connect to each other, based on bonding capital, popularity capital, and bridging capital. And together with Ahmed Allah, Kartika Ahuja, and Simsong Zhang, who are all former students, we show the impact of learning in network formation and in network science. Again, this represents state-of-the-art methods for network formation and strategic network formation. And this represents just a brief preview of our comprehensive work over multiple decades on modeling a variety of complex wire communication problems at different layers of the protocol stack effectively. Please take a look at our extensive work in this area using reinforcement learning in the single agent, multi-agent, and complex multi-agent setting, both cooperative and strategic. And you can find our publications at this website. Please revisit them because even though some of them represent work done many years back, a lot of this work I think is still pertinent today and can be improved and enhanced using deep learning technologies. So please take a look and reach out. I also would like to acknowledge that National Science Foundation has funded my research with the Career Award when I was a young assistant professor. So at the time at which wireless communication was not seen as a multi-objective strategic learning problem. So in early 2000, I received an NSF Career Award, which has funded this work and has led to this flurry of work in my lab. So I'd like to acknowledge the gracious support of the NSF Career Award and National Science Foundation, which has believed in this idea. And I'm happy that now, many years further,
almost 20 years further, this represents a vibrant area in communication systems using reinforcement learning. Thank you.
Okay, let's continue. Now we're moving to part 4 of this tutorial. This is the ICC 2021 tutorial, Online Learning for Wireless Communications, Theory, Algorithms, and Applications. My name is Tong Shen from University of Virginia. In the part 4, I will be discussing design examples in wireless communications using online learning tools that have been presented before by Professor Cem Tekin and Professor Mihaela Bendeshar. So what kind of applications are we talking about here? I want to emphasize that for the remainder of this tutorial, we will focus on applications of online learning, in particular, multi-arm bandits in wireless communications. The reason I chose to focus on multi-arm bandits is that MAB has a very good theoretical foundation where its application can be rigorously understood by analyzing the regret or the best arm performance. This is something that's very valuable when understanding its implications in wireless communications. On the other hand, I will also demonstrate using these design examples that a coupled relationship between online learning and wireless communication actually exists. We often thought of wireless communication as a consumer of online learning in the sense that online learning develops tools and the wireless communication just uses these tools. I also want to use these design examples to highlight the fact that the advancement of online learning itself actually is motivated by many applications, and the wireless communication can be one of them. So we should also be thinking about the unique features of wireless communications and how it can really feed back into the development of online learning. So this is basically the loop I want to talk about. Using online learning as a design tool to solve wireless communication problems, and wireless communications serves as a new application and provides new problem for online learning to study. Okay, so in the tutorial, we will focus on two wireless applications specifically to demonstrate this intimate relationship between MAB and wireless comm. One is spectrum engineering. This is one of the oldest and the most representative applications that are often used in multi-arm bandit papers. This mostly on spectrum access, dynamic spectrum access. The second is mobility management. So let me start with this application of spectrum engineering, in particular, the opportunistic spectrum access. This is a well-known problem. I don't think I need to talk too much for this audience. For comm engineers, this is a very well-known, a very well-accepted problem. We have a very crowded spectrum allocation as shown in this left figure. And on the other hand, as has been studied for almost 2 decades now, that the existing allocation of spectrum really is not fully utilized. In many situations, there is a strong emptiness in the broader spectrum. And the OSA is a way to dynamically probe and access these channels that are not used. So this is a fairly well known. And this is also something that's well known, but I want to highlight the fact that the channel selection is one of the problems that really bandit can help. So if you look at the top figure here, the spectrum occupation, this is a figure taken from the Valenta paper, 2010. The spectrum occupation really varies in time and frequency. That results in opportunities for secondary users to use the spectrum, as we all know. However, I want to emphasize that this is the time and frequency variation where the algorithm who attempts to use this unutilized system has to be highly dynamic. It is not stationary. It's not that you can fix on a channel and use it for a long period of time, or it is not that for a given time you can have a certain frequency that's always available. So in each time frame, the transmitter dynamically identifies a free channel to use by this channel sensing or probing. But as you can see in the bottom, that we have a problem of really selecting the channel, because you have basically many frequencies, generally speaking, and you need to figure out which channel you can use. And for example, how do I sequentially probe the channels can be one of the very earliest questions you can ask. If I'm given a list of, let's say, 15 channels, how should I start? And what is the order of the channels that I should pursue doing this channel sensing and probing? And as a matter of fact, the ordering really matters. We will be talking about it just briefly, but this is something that's intuitively understandable. And here I'm just almost like showing one particular problem in OSA that can already use basically online learning or multi-arm bandit algorithms. I mentioned before that bandit is a very natural tool for OSA because there exists this very strong correspondence between the bandit components and the OSA components. So you can think of arms in bandits as channels in OSA. Putting an arm corresponds to measuring the channel, and the reward you are getting really is the channel quality. For example, the SINR or the throughput of that particular channel that you just measured or you just used. On the other hand, we know that in bandits, we generally care about one of two things. One is regret minimization, and the second is to find the best arm. Regret minimization in the OSA case really corresponds to maximizing the long-term system utility. So basically, you keep using the channel and learning the channel along the way, and the hope is that for a certain period of time, you are going to accumulate a very large long-term system utility. The second part is this best arm identification, which tries to identify the best arm at either with a given time budget or with a given target precision probability. And this corresponds to selecting channel with the highest quality. And this is also valuable to consider best arm identification algorithms in the OSS setting. In fact, I will be talking about one example in this direction as a first example in this part of the tutorial. As I mentioned before, we really can just apply this, bandit algorithms to the engineering problems, but there's often the case that standard MAB really cannot be directly applied, or they're not a perfect match. Why? Because the COM problems have their own constraints and objectives. They do not sometimes match with what the standard MAB really aims to solve. One particular example, again, as I said, I will discuss first, is this good arm identification versus the best arm identification problem. And this is based on our GlobeSIP paper. The second, which is very recent and very elaborative, is a concept called the federated bandits. And this is a shining example of developing bandit algorithms that are actually motivated by requirements in the wireless communications. And this is attempted to this attempts to solve the so-called network listen problem in channel selection in a cellular network. So we'll be discussing this too. These two are based on two of our recent papers in IEEE and AI stats. Okay, so this is the first part of the application. The second part of the application will be on mobility management. Again, we will be discussing two specific results. One is that surprisingly, there is a relationship between 3GPP mobility protocol, which obviously is developed without any input from multi-arm bandits. I don't think the engineers who developed the 3GPP mobility protocol really thought about bandits in the first place. However, as it turned out, their philosophies have a striking similarity. And in fact, you can make a corresponding, you can actually make a correspondence between these two, as I will discuss shortly. Last but not the least, I will show one example using cascading bandits to construct the efficient neighbor cell list, NCL, for mobility management. Again, these are based on the following three papers, and please refer to these papers if you have more detailed questions. I will not be able to discuss the details given the time constraints of this work, but I hope to highlight the key ideas and contributions of this literature. Okay, the first example is about using the so-called good arm identification for OSA. So this problem, in fact, is a very engineering specific problem. We know that from the concept of best arm identification, it matches very well with identifying the best channel for from a given set of channels. So arm selection for OSA really can directly use existing best arm identification algorithms. But as we know from the bandit literature, even the optimal algorithms for best arm identification may have very slow convergence. This is true, especially when the game is hard. When we say the game is hard, what we really mean is that one suboptimal arm or several suboptimal arms are very close to the best arm. Let's say you have a best arm, let's say arm 1 with channel quality or the arm average reward of, let's say, 0.8. Let's say you have a second channel that is very, very close to the first one. Let's say it has a channel quality of 0.7999. So from an engineering point of view, one would say that these two channels really have no difference. They are very close to each other. Using one or the other has very little, if any at all, difference in practice, right? But for the best arm identification problem, however, this rigor actually works against us, because in this case, the algorithm would take a significant effort trying to figure out that one channel is slightly 0.0001 better than the next one. And this is when the game is really hard, and this is when the algorithm, even the optimal algorithm, has very slow convergence. So clearly, we ask the following question: is it really necessary to spend resources from a practical point of view, from a wireless communication point of view, from an engineer point of view, that to spend these resources distinguishing the best channel and the next best channel that is, let's say, 99.999% of the best one? The answer is no, practically speaking, right? So we shouldn't be using best arm identification in this case. Instead, we propose to look at this problem from a different angle. We are saying that, you know, the goal should be to find a good enough channel, but we want to find this channel efficiently. So we are in some sense sacrificing the optimality a little bit, but we want to gain something in terms of the efficiency of the algorithm. So this is really what this work is about. So let's look at a little bit of the detailed design. So let's say we have a set of candidate radio channels, let's say channel 1, 2, 3, 4 until capital K. And we have a channel quality feedback. At time t, channel I has a feedback of Ri of t. So this is a random variable with a mean value, let's say mu I. So this random variable could be, let's say, the signal to interference plus noise ratio, or the throughput, or the instantaneous channel capacity, so on and so forth. So we make this general, let's say, just using a random variable RIT with a mean value of mu I. And in addition, we define a minimum acceptable performance threshold for the user. Let's say this is tau. So what is this really about in practice? This can be thought of as, let's say, the minimum rate requirement for a given QoS class, or the maximum delay that can be tolerated for a given application, so on and so forth. So with this given threshold, now our goal is not to identify the best channel. Our goal is to output a channel at the end of the given, let's say, given time, capital T, and we want to make sure that this is good enough, meaning that the output channel has a mean reward value that is higher than tau with very high confidence, meaning high probability, okay? So this is our design objective. So putting this in the bandit terminology, the arms are the K arms, 1, 2, 3, 4, 2K. The action is to choose a channel, I of T, from this set of arms to do channel management or to sense. The reward is the corresponding channel quality feedback, R, sub I of T at time T. And this is a random variable that is drawn from the distribution of that particular action or that particular channel based on the hidden distribution of mean value of mu of I of T, okay? And this is obviously unknown. The goal is to minimize the error probability ET, which is outputting a channel whose actual mean value is not above tau, which is the threshold we were given for the algorithm, okay? So this is a bandit model. And we proposed an algorithm called the good channel identification, GCI. So a pseudocode of the algorithm is given here, and more discussions can be found in the GlobeSIP paper. I want to just emphasize the design philosophy here. This is very different from identifying the best channel. First of all, we are constructing confidence intervals that actually centers around the sample mean of mu IT, both upper and lower. So we are having upper confidence interval and lower confidence interval. basically centered around the sample mean. And then we're computing two metrics. The first is called the I sub t. So what is I sub t? This is the minimum upper bound of the gap compared to the empirically optimal channel. So we are basically trying to look at the minimum value of the upper confidence bound minus the empirically best channel at this moment. The second is UT is the estimated optimal channel that is not IT. So, removing IT for the remaining set of channels, what is the optimal channel that is estimated to be the best so far? So we want to select the most uncertain channel between these two for exploration in the next time slot. And by doing this, we are balancing essentially identifying a good channel versus accumulating knowledge about channels that could potentially be satisfying our requirements. Okay. Again, the details of this algorithm can be found in our paper. And let me give some theoretical results here. Again, as I said, the reason that we like Bandit for this type of problem is that you have the ability to derive rigorous performance bounds. So we have a theorem here, which seems very complicated, but the bottom line is that you see this error probability term that decays exponentially with this capital T here. Okay. So as you have basically, this is in fact, if you compare this, error probability upper bound, it is much faster comparing with the best arm identification problem. And this is mainly because of this smaller hardness quantity H1. So if you look at H1 here, we're not looking at the channel, again, hardness based on the best arm and let's say the second best arm. We're looking at this as a bounded term that is actually, again, directly related to the threshold. So you have this, threshold effect that's taking place here, but also you have this other terms that actually raises your threshold in some sense. That gives you kind of, less difficult game comparing with the original best arm. So lastly, let's look at some numerical results. So this is a fairly simple simulation. We are assuming that there's a given square area where we have users who are randomly jobbed in this area, let's say following this PPP process with a given density. And for every possible channel, we're going to job this user with certain parameters. So different channels will have different users who are already there. This can be considered as the primary user. And then at the center of the area, we're going to job our target user who needs to run this algorithm, the GCI algorithm. And we are computing the interference based on the pass loss model. We are not taking into account any other randomness such as shadowing or fading. And the feedback is really the instantaneous channel rate. Okay, so with this very simple simulation setup, as you can see from the figure, we have two different variables. First of all, two different thresholds of tau, 6.5 and 3. For both of them, you can see that the uniform algorithm, which is basically to look at this channel uniformly, basically one by one, and this is what we do today, basically doing channel sensing, right? You just sense the channel sequentially. And the pink one is this GCI algorithm that was shown in the previous slide, and the blue line is the so-called AT. AT stands for anytime. So this is a variation of the GCI algorithm where we do not have the a given time horizon capital T. Nevertheless, as you can see, both algorithms are better than the uniform strategy, and the anytime algorithm is also better than the fixed T. And in addition, as you have a higher threshold, obviously you're going to have a worse performance. On the other hand, if you have a smaller threshold, it's much easier to identify one channel to satisfy the requirement. So the convergence is extremely fast for the dashed curves. That's all for this topic. Okay, so let's move on to the next one. Okay, next we want to talk about another application-driven bandit development called federated multi-arm bandits. So this motivating wireless application is in fact very, I think, would resonate well with the engineers who work on wireless network optimization. So basically, as we all know by now, that cognitive radio and the dynamic spectrum access is often used as a motivating example for MAB research. And this is for very good reasons. Because generally speaking, you can think of the player who plays this bandit game, let's say as a base station, or a device that also works. So either way, let's say the base station wants to use the statistically best channel for communication. So he is given basically a set of channels, let's say channel 1, 2, 3, 4, all the way to capital K as shown here. So if this base station has to commit to one channel to use for, let's say, a certain period of time, then obviously, if we know the channel availability or the channel quality, if you will, that behaves like this, then obviously channel 3 is the best choice. We should always use this channel. Through, let's say you are fixed to just using one channel. Let's say you're trying to do broadcasting or something like that. So this is really what the base station can do at its best. On the other hand, this knowledge is often not known by these by the base station. So he has to basically find out through the exploration and exploitation. So this is why it's a good match to the stochastic multi-bandit problems. Okay. So so this is basically the first, I think, the application that matches wireless channel selection to multi-bandits. But if we are looking at this from a cellular network point of view, where the base station really covers a certain coverage area, right? So it has a, let's say, a coverage area like this. Then if we know everything about the system, the base station should choose a channel where the availability is actually computed across the entire coverage area, not just at the base station's location, right? Because the goal is for the base station to serve this area, not just the base station itself. And since we generally do not know where the user may actually exist, so we have to basically make sure that our coverage is entire coverage area is well served. So, to restate this, the base station still wants to use a single best channel for the entire area, but the ground truth now is defined as the so-called global availability, which is the average over the intended coverage area. So if you know the channel availability function as as a function basically of the location X, then you should do this integration to find out on average which channel is the best. The challenge, however, is that base station cannot really get this information alone, because base station is fixed at one location. And this is also the shortcoming of the so-called network listen mode for the base station. This cannot solve the problem. On the other hand, if you want to solve this problem rigorously, you need continuous sampling of the coverage area, which is also, generally speaking, not possible. Lastly, as the other online learning applications, we always want to control the learning cost so that we get a good conversion speed. The solution here is something that also we all know very well for wireless engineers. The base station is fixed at one location, but we have users that are randomly distributed in the coverage area. So we should rely on them to measure the channel and report back. The difference here is that conventionally, we would ask this, let's say, clients 1, 2, 3, 4 to capital M, which are geographically spread out in this coverage area. We would generally ask these clients to measure every single one of these channels. And then we would ask them to report the measurement back to the base station, and base station computes the average and then selects the best channel. What we are going to show here is that this is highly ineffective. In fact, you do not need obviously the clients to measure every single channel. Certain channels can be eliminated really quickly because they cannot really be the best global channel. And that is where the multi-banded algorithms really are better than this kind of uniformly sampling approach. It would also save a lot of cost from the clients. It will also reduce the delay, so on and so forth. Okay. So what is federated bandits? This is a new concept that we have been developing over the last year. The key observations here are the following. The server, which is base station in this case, wants to learn the global model, but it lacks direct access. It cannot really access this global bandit model. The client, in this case, is the user equipment, can play the local bandit game because the client can only measure at its own location. So it only has local observation that is a noisy part of the overall picture. In addition, the local models for different clients are generally heterogeneous. So if the clients are at different locations, they will generally see a different distribution of the channel availability. So neither the base station nor the client, the UE can solve the problem by itself. And we will need coordination between the base station and the UE. And this actually, if you look at this list of observations, it is very much like federated learning. This is why we call this federated bandits. The challenges here is that obviously we still want to have the continuous ground truth. That is our design goal, but we only have discrete sampling. So how can we use discrete sampling to approach the continuous ground truth? The second is that there is often misaligned objective between local bandit model and global bandit model. And for example, in the previous figure, right, we know that the overall, for example, channel 3 is the best one. But as you can see here, channel 3 is almost never the best one in any of these shown examples. So this tells you that there is often this misaligned objective from the local model and the global model. Okay. So we are studying federated bandit here. And how do we model this global local relationship? We are taking actually 2 attempts. The first attempt is to view this, the local models as random variables, which are drawn IID from a latent global distribution. So the latent global distribution is really the global channel availability, and the local channel availability model is really a random realization from the global model. So this is what we call the approximate model. And in fact, this is a much more difficult problem than the second one that I will briefly mention at the end. So let's say we have a global MAB model with k arms. Think of that as k channels. So arm k has a mean reward mu k. Think of that as the, let's say, the average data rate on this channel. So then if we have this global channel availability, I know, again, channel 3 is the best one. Okay, maybe it has the highest average data rate of 5 megabits per second, for example. Okay. So how do I generate the approximate local models? Okay, so let's say I have this global model. Again, it's a latent model, so we don't know it, we need to learn it. But for this latent global model, I would generate, in an IID fashion, local models where every local model is generated based on this global model following a certain distribution. So let's say, the first channel, mu1, has, let's say, a global channel availability of certain value. Then I'm going to generate a mu11 for client 1 based on a distribution whose mean value is mu1. I'm not going to specify this distribution, and this is actually not very important, but the relationship is really that it is a realization from a distribution whose mean value is mu1. And this goes with other channels as well. And you do that for every client, okay? So this is how you generate the local model. So global model is really a fixed ground truth, but it's unknown. And the local model is a random sampling of this unknown global model based on a latent distribution. So basically, as I said, mu km is an ID sample from a latent distribution with mean mu k. All right. So this is the approximate model. And how do you solve this approximate model? The first challenge is that the average local models is not really the global model. In fact, you can easily argue that even if you have perfect knowledge of local models, we will have an average local model of this, right? If I know every mu km perfectly, for, let's say, channel k, the average value is going to be the true local mean value averaged over the m clients. And this mu k hat is not the same as the true mu k because these are realizations from the true mu k. So they do not necessarily give you any finite sample mean, does not necessarily give you the true mean, okay? In fact, the more difficult part is that the optimal arms in both models may not even be the same, let alone that their values are not the same. Since mu k hat is not necessarily the same as mu k, obviously for the ground truth, the best channel, let's say, is k star. Then, based on mu k hat, you're gonna compute another best channel. These two may not necessarily be the same. And if they're not the same, there is no way you would find this optimal global channel by using these values from observation from the local models. So that is a fundamental problem. So we need to ensure that the optimal arms are at least the same. This is the bottom line. The idea is to involve more clients, right? Because as you have more and more clients, and as M increases, we know that mu-k hat approaches the true mean mu-k. So as long as you have sufficiently many clients, mu-k hat is close to mu-k, and you should always be able to separate the global optimal arm. Okay. That brings the second another challenge. How many clients are needed? I mentioned that you should have sufficient many, but what is sufficient many? If you have an undersampling, then you cannot guarantee matching optimal arms. But if you have oversampling, then you bring an unnecessary communication cost, because remember, all of these clients are going to not only just measure this channel, but also communicate the result to the base station. So this will bring unnecessary cost. So we need sufficient but not excessive amount of clients. But what is this? If you assume perfect knowledge of the model, then you can use concentration inequalities. It tells us that the exact order is like this: log KT divided by delta square, where delta is the suboptimality gap. Again, by now you know what this gap is. It measures the difficulty of the game. Okay, but again, in reality, we do not know delta, right? And this is based on so the M is really based on an ideal situation where you assume that you know the game, but we do not know the game to begin with. So how do we solve this problem? The second challenge is to balance communication and necessary coordination. So this is similar to federated learning problems, where you want to minimize the communication cost while getting a good convergence. So the key ideas of FMAB is that first of all, we do periodic communication. This is just like a FL. And secondly, we're going to gradually increase the number of clients after each communication round. So in the engineering sense, we are starting off with a small set of users in the coverage area to do measurements. And then over time, we're going to admit more UEs to do measurements or to play this bandit game for us. And we're going to stop at a certain point, not admitting more users. So this is also a different philosophy as in the conventional method, where we have a uniform number of clients. We use that throughout the game. Okay. The benefit here is that we can actually learn suboptimal gap along the way. So this ensures what our previous goal, which is to have sufficient but not excessive amount of clients. And this simultaneous handling of client sampling and arm sampling leads to this WCB technique. Again, I'm not going to talk about details here, but let me just give the algorithm. Okay, this is a phased algorithm. Let's say in phase P, the server, which is base station, would admit a new set of clients into the game. Basically, you ask a new set of, let's say, user equipments to do channel management for you. And every client will pull the active arm in active arm set a certain amount of times, and then send the updated arm statistic to the server. And server receives this updated statistics and run an arm elimination algorithm. Again, the details can be found in the IEEE paper, which uses WCP principle to eliminate suboptimal arms. And then it's then updated. So this is a way basically to eliminate those channels that cannot be globally optimal. So we are going to shrink the set of channels for the users to explore. This is the key idea. And then we send this updated list to clients, and clients receive the updated list from the server, and then we go to the next phase. So this algorithm, again, has very good theoretical guarantee. And this is the upper confidence bound that we constructed from both arm sampling and client sampling. And our regret analysis actually shows that we have an order optimal regret for the approximate model. So this is really a very good behavior. Lastly, let me talk about the extension, because the approximate model is not very realistic in general, but it actually lays the foundation to develop something for the so-called exact model. The exact model is that when the global model is the exact average of local models. So let's say you have 10 users in this coverage area, then my global model is going to be the exact average of these 10 local models. So in this case, we'll have a fixed number of clients. So we don't have to scale the clients to solve this approximate model. And you can directly degenerate the previous algorithm into Fed1 UCB that you only have to do basically arm sampling. So this gives you a much easier problem to solve. Okay, that's it for now, and we'll move on to the next topic. We are at the last example in part 4, in this example, we'll be talking about the equivalence of 3GPP mobility protocol and multi-arm bandits. And then we will talk about a new algorithm based on cascading bandits for mobility design. So let's talk about the mobility for a second. Mobility is a task that determines whether UE needs to switch serving base stations, and if so, which base station to switch to. There's a long line of literature, but mainly if you look at the tools that are used in solving mobility problems, they are mostly based on game theory or optimization theory. The problem with some of these approaches is that the current view of mobility is still largely myopic or short-term. And they also assume known deployment information as static system dynamics, which we all know are not true. The contributions here, I would say mainly is the first one. We have established an equivalence between 3GPP mobility protocols and the bandit learning algorithms. In particular, we showed that the original 3GPP mobility protocol is really a realization, an instance, I would say, of epsilon greedy bandit algorithm. Once you realize this equivalence, then we can leverage the theoretical results of MAB, in particular related to epsilon greedy bandit, to analyze the performance of the previous 3GPP protocol, understanding their short limitations, and then making improvement. Okay, so let's say we have M small base stations and M UEs, and let's consider a static or slow-moving UE case. So this is mostly an association problem, okay? And the static and slow-moving UEs allow us to consider stationary distributions of the rewards. And if they're not satisfied, if these conditions are not satisfied, we have to consider time varying or non-stationary rewards. That would bring us to the non-stationary bandits, which we also have some other works on that topic. But in this part, I will limit myself to the stationary reward distribution for every base station. The handover protocol for a 3GPP, initially, they are based on comparing a few things. One is the serving base station. The ISRP is really the signal quality, and there is the hysteresis, and there is also a threshold. The target base station has something similar, the measurement plus some kind of a threshold. Then we are basically comparing these two metrics. If the serving base station is larger, has a large metric, then we stay on serving base station. But if a target base station has a larger value, then we will switch to that base station. This was the original 3GPP mobility decision metric, and after many years, there are different enhancements. But so far, the philosophy remains the same. We're comparing certain things of the serving base station to certain things of other base stations and make decisions based on that. And this principle is myopic, as you can see. It depends on what happens right now. It does not really take into account the future behaviors. In other words, if for a particular user, let's say UE, if the UE knows which base station is going to be the best for in the near future, then this UE would have selected this base station and stay on it. Even if, let's say, at this moment, that base station does not have the highest signal quality. Because generally, the goal is not really for the UE to stay on the base station that is the best right now, but rather the UE wants to select a base station that is good or near optimal for the near future. This would allow the UE to stay on this base station and maintain a stable communication rather than switching between different base stations from here to there. Again, since we consider static slow-moving UEs, it's reasonable to consider that every base station has a signal quality, or their rewards follow some statistical distribution that do not change within the time of interest for the algorithm. And the UE is trying to get good performance while also learn this mean reward information of the base stations. And this is the bandit problem. So we can view every base station as an arm, and the UE's performance is going to be the reward distribution. And if we hand over a UE to another base station, basically means that we're going to sample the reward distribution of that corresponding arm. So we are going to be choosing a different arm to pull and get a reward from its hidden realization, its hidden distribution. Okay, so now comes our main result. For stochastic bandit and 3GPP mobility, If you think about this as a bandit problem, then naturally you will think of the stochastic bandit algorithms, greedy algorithms, epsilon greedy algorithm, softmax, or UCB type of algorithms. The natural idea is to apply some of these methods to mobility. Well, as it turned out, 3GPP already does something like this, but unconsciously, right? Why? Because our main result actually says that the epsilon greedy algorithm from MAB really is the same as the 3GPP protocol. Why? Because if you compare them side by side, the probability for each arm really is corresponding to measuring the RF conditions, let's say RSRP or RSRQ. Then the probability of selecting a particular arm in the epsilon greedy algorithm really corresponds to, once you are staying on the best base station you think you already have, then you would just occasionally move away from that base station or that arm to explore the other arms with a probability epsilon. And what is this probability in 3GPP protocol? Well, this probability is the probability that the other RF conditions really got triggered. If you are already staying on a serving base station, and then another base, let's say another base station has an RSRP value that is higher than your value plus some threshold, then you would trigger handover to that base station. And this can be sort of as a random event in RF. So this is how we actually connect these two and use epsilon greedy algorithm to model 3GPP protocol. The importance is really that once you have this equivalence, then you can use MAB theory, which has rigorous theoretical proof of the suboptimality of epsilon greedy and the non-convergence of epsilon greedy as well. The non-convergence part really explains why you cannot really solve the FHO problem in the previous 3GPP protocol. Okay, so how to improve? The first idea is you can use better algorithms. You don't epsilon greedy is not a very good bandit algorithm. You can try to improve that by using better algorithms. Okay, we did not go this route. What we did do is the second idea, which is to explicitly punishing switching. To do that, we have to incorporate the so-called switching cost in the standard MAB problem. This switching cost forces the new algorithm to introduce the concept of blocking or batch exploration. The size of the block also increases over time. So intuitively, in fact, if you think about it, these ideas have already been used one way or another in the current FHO solutions in 3GPP. But we'll see that there are important design differences. So what is done in the engineering solution so far? The heuristic algorithm works like this. You would declare for FHO if a certain UE switches more than Y times over the past X minutes. And once this happens, you will say that let's adjust the UE handover parameter to make it even more difficult to switch. And this solution is actually very similar to MAB-based method, where you will see some frequent switching at the very beginning, right? Because you haven't really accumulated enough evidence to declare FHO. Once you pass this phase, you will slow down, and then it will converge. And we can again show that this is equivalent to using the switching cost and doing this blocking design. And with that, you can also analyze the performance rigorously using the MAB theory. Lastly, I'm just showing a quick simulation result showing the CDF of the number of handovers. I'm ignoring the setup here. You can find the simulation setup in the paper. But what you can see is that, yes, 3GPP frequency handover solution does improve over the original protocol, but our algorithm, which uses this rigorous blocking methods that designs the length of the blocks and how often and how quickly you increase this block length, can further improve this handover performance. All right, let's move to the last part, which is the cascading bandit approach to efficient mobility management. This is a particular problem for the so-called ultra-dense networks, UDN. We have user association and mobility management problem. The challenge is, as I mentioned before, UE has many choices, and the channel states are time varying. And in fact, a very small physical movement may lead to very large channel condition changes. So we have the 3GPP based solutions already explained before. We also have the optimization based methods that you can try to, first gather this UE and base station information and then maximize a certain system utility. Our approach here is actually to look at this from a bandit learning point of view, to learn the system statistic based on historical measurements and adjust decisions on the fly. So as the section title suggests, this is based on something called the cascading bandit. So what is cascading bandit? The classical bandit, the cascading bandit model really originates from the so-called click-through rate problem in recommender systems. So the problem is like this. The objective is to have a list of items. Let's say you have a total K items. How do I determine a list of K items without any prior information to recommend to a given user? Without any prior information, obviously you do not know which L items are the most popular for the user. So you have to learn this on the fly. So basically what you can do is that you can start with, let's say, a random L items, and then you give this L items to the user, and then you observe the behavior. The user would look at this item one by one, right? So let's say the first time the user looked at the first item, did not click on it. Second, also pass. Third, pass. The fourth one, the user clicked to watch this movie. And then what you learned so far is that the first three items are not attractive to the user. The fourth item is attractive to the user. And there's no information for the last two because the user did not get a chance to examine these two. And then you run your algorithm to get another list of, let's say, 6 items recommended to the user. And then you look at what the user does. And then you get another run of information, and so on and so forth. And gradually, you would kind of converge to a good list of L items out of the K items, where it has the L highest click-through rate. Okay. This is the classical cascading bandit model, but this one has some issues, especially if you want to use that for our mobility problem. First is non-additive reward, because it will get reward 1 only if one of the items is clicked. If none of the items is clicked, there is always a reward 0. Second is this hard constraint on the size of the list. You have to have a, you have to know this variable or this parameter L beforehand. So what we do here is that we, in order for us to really utilize this for our own mobility problem, we have to make some changes. The first change is that we are going to relax the constraint of the size of the list. The second is that we're going to impose cost of putting arms, because this is the same philosophy as the previous example. Putting arms in this case means we're going to switch to another base station, and this obviously involves cost because we do not want this to happen too often. Okay. I'm going to skip most of this next few slides, but I just want to mention that for the cascading bandit problem with cost, this is very non-trivial to solve. Again, this is motivated by our mobility problem, but we have to solve the bandit model first. As it turned out, this problem is non-trivial, but it has a very beautiful and simple solution. Theta here can be viewed as the probability that, for example, the base station is the optimal, is the best base station, and Ci can be viewed as the corresponding cost of using this base station. And we have established this simple decision rule, which is to use theta I divided by Ci as the index, and then you compare the index of all of these K arms or items, and then you rank them. You only pick the ones that have this ratio are above 1. That turned out to be the optimal solution. And once these are unknown, which is in our case, then you have to learn this on the fly. So this is a so-called cost-aware cascading UCB algorithm, or CCUCB. We are going to estimate the UCB of theta I and LCB of Ci each time. Again, if you look at this from the mobility point of view, you are estimating an optimistic version of the channels, of the base stations quality, and a pessimistic version of the cost. And then theta I divided by Ci gives you an optimistic version of the overall metric, meaning that I'm taking an optimistic view of the base station, and I'm taking that across all base stations. Then I'm going to take the one that has the highest value of this. I'm going to rank that as the highest. Okay. So how do I apply this to the mobility management problem? And in this particular example, we are not directly with mobility management, but rather we are considering how to construct an active neighbor cell list, NCL, for each base station. This is important because MME maintains such list, an active NCL for every base station. And when a handover is triggered, MME will send the list to the UE, and UE would examine this base station in the list sequentially until it basically chooses the first suitable candidate base station based on their measurements. And if none of the candidate base stations satisfy the handover condition, the UE will stay on the previous serving base station. In this case, the feedback from UE to the MME is the handover result and the probing cost. For example, the delay or the energy cost, so on and so forth. The advantages here is that with our method, we can actually have a very small active NCL list, as opposed to populating all known possible neighbor cells. This is very useful in an ultra-dense scenario. The second is that the base stations on the list are ordered, so they have to be examined one by one. This would help accelerate the handover procedure. You don't have to basically check too many candidates. And based on our CCB algorithm and its analysis, we actually can derive rigorous theoretical performance guarantee that CCB NCL really inherits the order suboptimality of CCUCB. We also take into account a practical situation where feedback is delayed, because in reality, the mobility result is not immediately known from the UE to the serving base station, but rather, or to the MME, but rather there may be some delay later on where this result becomes available to the MME. But we show that this actually does not really affect the performance significantly, as long as the delay is not too big. The experimental results are very promising. We see that our CCUCB algorithm has a regret that grows sublinearly in time. This is consistent with our upper bound. Additionally, the delayed feedback has very little impact to the overall regret. Lastly, we also introduced the so-called missing feedback, meaning that the handover result is not received by MME. This we also show that it has some performance degradation, which is understandable because the MME cannot really learn from this missing feedback. But overall, our conclusion is that this is a promising direction to reconsider how we construct neighbor cell lists and how we do mobility management. With that, I conclude part 4 of this tutorial. And overall, we have given basically two big parts of online learning and its application in wireless communications. It is our hope that you find this tutorial helpful, and we believe that there are many things that can happen in this direction. On the one hand, we believe that there are many tools that are known in the online learning, for example, bandits or reinforcement learning community, that are still kind of that are like hidden jewels for wireless communication engineers. We're not aware of those tools. We are not trained to take advantage of those tools, but it's time for us to think of those tools and to explore those directions. On the other hand, for researchers who are interested in online learning, wireless is a very good example to give you new problems and the new models to study. And this interaction or this loop between online learning and wireless communications is really something I think that's interesting and is worth further investigation. With that, I conclude our tutorial, and we'll be happy to take questions. Thank you very much.